Imagine wiping away everything you know, the screen you are looking at, the chair you are sitting on, even the air you are breathing. All of it vanished. Now, erase the earth beneath your feet, the sun lighting the sky, and every distant star shimmering in the cosmos. Finally, erase space itself. What remains? Absolute nothingness, a complete void. In the blink of an eye, this emptiness, this sheer absence of everything, transforms into a universe brimming with infinite possibility. This is not a story from a science fiction novel. It is the true story of our cosmos. Join us on an extraordinary journey through the vast expanses of space and the mysterious corridors of time as we explore how everything, every star, planet, and atom began from nothing. In scientific terms, nothing means the total absence of matter, energy, and even the very fabric of space and time. This idea is mind-bending. It challenges our everyday experience, where objects, forces, and interactions constantly surround us. But in physics, nothing opens a profound door to questions about the nature of existence itself. Surprisingly, the nothing scientists describe is not always truly empty. Quantum physics reveals that what we think of as a perfect vacuum is alive with activity. Tiny particles blink into existence and vanish in moments, driven by the strange uncertainties of energy. This ceaseless dance is known as quantum fluctuations, and it turns the idea of a true void upside down. What seems like emptiness is actually filled with potential and hidden energy. This means that even nothing holds its own complex secrets, inviting us to reconsider what we mean by empty space. When we look to the origins of our universe, discussions often turn to what came before the Big Bang, the moment everything exploded into being. Some cosmologists suggest that the universe emerged from a state of nothingness, a place where the laws of physics, as we know them, did not yet exist. This thought stirs profound questions. How can something arise from nothing? What does it mean for causality, the idea that everything must have a cause? These puzzles push the boundaries of science and philosophy alike. The transition from nothing to the universe we live in may involve processes we are only just beginning to understand. In this light, nothing is no longer just a simple void. It becomes a concept rich with mystery, complexity, and wonder. It forces us to think deeply about the fabric of reality and challenges our grasp of existence itself. Physicists describe the universe before the Big Bang as a singularity, a point where everything, matter, energy, space, and time, was squeezed into an unimaginably tiny volume. At this singularity, densities reached infinity, and the laws of physics as we know them break down. It is a realm beyond our current understanding, where all known rules collapse and where the story of our cosmos begins. From this singularity, the universe burst forth, expanding and evolving into the vast, awe-inspiring cosmos we inhabit today. The journey from nothingness to everything is the greatest story ever told, and it continues to unfold with every new discovery. In the vast and mysterious saga of the cosmos, the Big Bang Theory stands as one of the most profound explanations for the origin of everything we know. According to many cosmologists, the universe began as an unimaginably hot and dense point, a singularity so extreme that it defies our everyday understanding. Then, in an instant, this tiny compact point experienced a rapid expansion, giving birth to space, time, and all matter. Yet, the moments before this colossal expansion remain shrouded in mystery. There is no direct evidence to reveal what truly existed, or whether anything even existed, prior to the Big Bang. This enigmatic beginning continues to ignite intense curiosity and debate among scientists and philosophers alike. The notion of a primordial singularity raises fundamental questions. What conditions prevailed in that infinitesimal moment? Could time itself have existed before the Big Bang, or did time only come into being as the universe expanded? These puzzles challenge the very limits of human understanding. Some theories suggest the universe emerged from a quantum state, where the usual rules of physics give way to the strange and counterintuitive behaviors of the quantum world. Others propose a cyclic cosmos, where universes endlessly collapse and rebound in an eternal dance of death and rebirth. Still more, envision our universe as one bubble in a vast multiverse, with countless other universes existing simultaneously, each with its own distinct laws and realities. The quest to comprehend the state of the universe before that monumental event drives much of modern cosmology. Researchers use sophisticated theoretical models and observe cosmic clues left in the fabric of space to piece together this cosmic puzzle. Though definitive answers remain out of reach, the pursuit itself broadens our understanding and invites us to contemplate the very nature of existence. This quest leads us to confront an even deeper mystery, the concept of true nothingness. True nothingness is a profound and challenging idea. In strict scientific terms, it is often seen as a theoretical notion rather than an achievable state. Quantum physics reveals that even what we think of as empty space is alive with activity. Tiny quantum fluctuations continually produce and annihilate particles in the blink of an eye. What seems like a void is actually a restless sea of virtual particles and energy. This challenges our intuition and forces us to rethink the meaning of emptiness. Philosophically, many argue that true nothingness cannot exist because it would lack any properties, dimensions, or even a framework against which to define existence. To even ask whether nothingness exists is to imply some context or background in which nothing could be understood. Some philosophers go so far as to say the question itself is a contradiction, since understanding nothing requires a something to compare it to. From the standpoint of cosmology, the origins of the universe further complicate the idea of nothingness. Theories about the birth of our universe often involve states or conditions radically different from anything we observe today. These states are governed by physical laws or energies that defy the idea of absolute emptiness. Dark energy and the cosmological constant hint at hidden forces that might constantly shape the fabric of what we consider empty space. Over time, our understanding of nothingness has evolved dramatically. In ancient Greek philosophy, nothingness was often seen as the opposite of being. Philosophers like Parmenides argued that nothingness simply could not exist, insisting that we can only speak meaningfully about what is. The void, or the absence of being, was dismissed as impossible. Medieval philosophy and theology introduced new dimensions to this debate. The concept of creation ex nihilo, creation from nothing, became a central religious idea, suggesting that the universe was brought into existence by a divine power from a state of absolute nothingness. This gave nothingness a spiritual and metaphysical significance beyond mere absence. With the rise of the scientific revolution in the 17th century, thinkers like René Descartes helped shift the discussion from purely philosophical and theological realms toward empirical science. Newtonian physics introduced the idea of a vacuum, a space devoid of matter, sparking initial explorations into the nature of emptiness in the physical world. This marked a turning point in how humanity approached the question of nothingness, blending observation with deep philosophical inquiry. The study of nothingness, far from being an abstract or trivial pursuit, continues to reveal profound insights about the nature of reality. Whether through the lens of quantum mechanics, cosmology, or philosophy, the exploration of what it means to be and not be pushes us toward a deeper appreciation of the universe's mysteries and the fragile, awe-inspiring nature of existence itself. However, it was not until the dawn of the 20th century, with the revolutionary development of quantum mechanics, that our understanding of the concept of nothing underwent a profound transformation. Quantum physics unveiled a startling truth. Even what we perceive as empty space is far from empty. Instead, it teems with energy and fleeting virtual particles that blink in and out of existence in a ceaseless dance. This discovery shattered long-held beliefs about absolute emptiness, challenging the idea that nothing truly means the absence of everything. The revelation that empty space brims with potential energy opened new avenues of thought about the very nature of the universe. Today, the investigation of nothingness stretches beyond physics into the realms of cosmology and philosophy, blending the tangible with the metaphysical. At the heart of this inquiry lies the phenomenon known as quantum fluctuations in a vacuum. Quantum fluctuations describe the spontaneous and temporary emergence of particle-antiparticle pairs from the vacuum, pairs that appear and vanish due to the inherent uncertainty at the foundation of quantum mechanics. According to quantum theory, even the emptiest stretches of space contain an omnipresent energy field that allows these ephemeral events to occur. This challenges the classical view of a vacuum as a simple void, revealing it instead as a dynamic environment buzzing with activity. These fluctuations highlight that a vacuum is not truly nothing. Instead, it acts as a stage where virtual particles materialize for mere fractions of a second, shaped by the uncertainty principle. This principle states that certain pairs of physical properties like position and momentum cannot both be precisely known simultaneously, permitting these brief bursts of energy and matter. As a result, even in what seems like empty space, a foundation of energy and possibility endures, meaning absolute nothingness, devoid of all properties and effects, remains elusive within our current physics. The significance of quantum fluctuations extends far beyond theoretical physics. In cosmology, they play a vital role in shaping our understanding of the universe's origins. It is believed that these energy fluctuations in the vacuum were instrumental in the moments immediately following the Big Bang, driving cosmic inflation, a rapid expansion that set the stage for the universe's evolution. Variations caused by these fluctuations seeded differences in density, which eventually gave rise to the vast cosmic structures, galaxies, clusters, and filaments that define the universe today. Thus, the vacuum, once thought to be empty, reveals a rich and complex reality. The universe, even in its quietest spaces, hums with potential and energy. This nuanced understanding complicates the quest to define what nothing truly means. The Big Bang Theory, the prevailing model explaining the universe's beginning, posits that approximately 13.8 billion years ago, the universe sprang from an unimaginably hot and dense state. This theory rests on several key pillars of evidence. One of the most compelling pieces is the cosmic microwave background radiation, a faint, uniform glow permeating all of space, which acts as a relic of the early universe's heat. Discovered in 1965 by Arno Penzias and Robert Wilson, this radiation's uniform temperature of roughly 2.7 degrees above absolute zero lends strong support to the idea that the universe expanded rapidly and cooled after its fiery birth. Another cornerstone of the Big Bang Theory is the red shift of distant galaxies, first observed by Edwin Hubble in the early 20th century. Light from these galaxies is stretched toward the red end of the spectrum, indicating they are moving away from us. This phenomenon suggests the universe is expanding. The relationship between the galaxy's distance and their red shift, now known as Hubble's law, implies that if we reverse time, all galaxies converge to a single point, underscoring the notion of a cosmic beginning. Furthermore, the abundance of light elements such as helium, deuterium, lithium, and beryllium throughout the universe matches predictions from Big Bang nucleosynthesis. This process, occurring in the first few minutes after the Big Bang, involved the fusion of protons and neutrons into these light nuclei. The observed ratios of these elements align remarkably well with theoretical calculations, further validating the model. Large-scale structures, including the distribution of galaxies and galaxy clusters, also support the Big Bang narrative. These formations trace their origins to the initial conditions established by the Big Bang and the subsequent inflationary epoch. Telescopes and cosmological surveys continue to map these cosmic patterns, reinforcing the picture of an evolving universe emerging from a highly concentrated state. Edwin Hubble's groundbreaking work laid the foundation for these insights. Before his discoveries, the universe was widely believed to be static and eternal. Hubble's observation that distant galaxies recede from us, manifest in the redshift of their light, revolutionized cosmology, suggesting a dynamic, expanding universe. Together, these discoveries weave a compelling story of cosmic history, painting a picture of a universe born from a singular event, evolving through time, and governed by laws that connect the realms of the very large with the very small. The journey from the illusion of emptiness to the revelation of a vibrant, energetic vacuum continues to reshape our understanding of reality itself. However, the idea that galaxies are moving away from each other carries a profound implication. If they are currently spreading apart, then at some point in the distant past, they must have been much closer together. This simple observation supports the concept of a definite beginning for the universe. The expanding universe model, built on this insight, set the foundation for what we now call the Big Bang Theory. According to this theory, the entire cosmos originated from an extraordinarily hot and dense state roughly 13,800,000,000 years ago. Hubble's observations were more than just measurements. They triggered a monumental shift in how scientists viewed the cosmos. Before his work, many believed in a static, unchanging universe. But Hubble's findings forced the scientific community to accept a dynamic, evolving universe, one in constant transformation. This change in perspective opened the door for physicists and cosmologists to explore new theories. These included ideas about cosmic inflation, a rapid expansion in the universe's earliest moments, the formation of cosmic structures, and the mysterious roles of dark matter and dark energy that govern much of the universe's behavior today. More than just observations, Hubble's discoveries highlighted a vital need, a comprehensive theoretical framework to explain not only the expansion itself, but also the universe's origin and long-term evolution. His pioneering work became a cornerstone that led to the widespread acceptance of the Big Bang theory as the leading explanation for our universe's beginnings. This shift profoundly influenced how we understand the history of the cosmos and its ongoing development. Right after the Big Bang, conditions in the universe were extreme beyond imagination. Temperatures soared to incredible heights, and matter existed in a state of unimaginable density. In those earliest moments, the universe was a blazing hot plasma filled with fundamental particles like quarks, electrons, and neutrinos. The temperatures were so intense that ordinary atoms could not form. Instead, particles continuously collided, annihilated, and recombined in a chaotic dance of energy and matter. As the universe expanded, it began to cool rapidly. This cooling allowed quarks to merge into protons and neutrons within the first few microseconds after the Big Bang. This rapid transformation laid the essential groundwork for nucleosynthesis, the process of building atomic nuclei. Within just a few minutes, the universe produced significant amounts of helium, along with traces of deuterium, lithium, and beryllium. These primordial elements still make up much of the elemental composition we observe in the cosmos today. Following this nucleosynthesis phase, the universe kept expanding and cooling. Approximately 380,000 years after the Big Bang, the temperature dropped enough to allow electrons to combine with protons to form neutral hydrogen atoms. This event, known as recombination, led to the decoupling of matter and radiation. Photons, particles of light, were suddenly free to travel through space unimpeded. This moment released the cosmic microwave background radiation, a faint glow that fills the universe and can still be detected by instruments today. Thus, immediately after the Big Bang, the universe was an incredibly hot, dense environment filled with energetic particles. Its rapid expansion and cooling set the stage for the formation of the first atomic nuclei, then neutral atoms, and eventually the stars, galaxies, and complex structures we observe across the cosmos now. Estimating the age of the universe is no simple task. It requires a careful blend of theoretical models and detailed astronomical observations. Today, scientists estimate the universe's age to be about 13,800,000,000 years. This estimate comes from multiple interrelated methods. One of the most important techniques involves studying the expansion rate of the universe, famously described by Hubble's law. By observing distant galaxies and measuring how much their light is stretched toward the red end of the spectrum, a phenomenon called redshift, astronomers can calculate how fast the universe is expanding. This expansion rate, known as the Hubble constant, offers a way to rewind cosmic history and pinpoint the moment when everything began, the Big Bang. This method provides a crucial timeline for understanding the universe's age. Another key approach comes from analyzing the cosmic microwave background radiation, the leftover heat from the Big Bang itself. Satellites like the Planck spacecraft have mapped this radiation with incredible precision, revealing tiny fluctuations in temperature and density. These variations carry vital clues about the universe's infancy and its subsequent evolution. By studying this background radiation, scientists gain a deeper understanding of cosmological parameters that refine age estimates and illuminate the universe's complex history. In this way, through the combination of observing the cosmos's expansion and decoding its ancient light, humanity has pieced together a remarkable story, one of an evolving universe born from a fiery beginning and continuing to unfold across billions of years. Additionally, astronomers use the ages of the oldest known stars and star clusters within our galaxy to help estimate the age of the universe. Take globular clusters, for example. These clusters contain some of the oldest stars ever observed, and their existence provides a minimum age for the universe because these stars must have formed after the Big Bang. By carefully studying the types of stars within these clusters and applying detailed models of how stars evolve over time, scientists can calculate how long these stars have been shining. By combining these stellar age estimates with other powerful methods, such as analyzing how the universe is expanding, observing the cosmic microwave background radiation, and measuring the properties of ancient stars, researchers reach a consistent and reliable estimate for the age of the universe. This comprehensive, multi-method approach ensures that the estimate is strong and considers a wide range of cosmic phenomena and scientific principles. This process forms the foundation of our understanding of the universe, rooted firmly in evidence and rigorous science. One of the most important pieces of this cosmic puzzle is the cosmic microwave background radiation, or CMB. The CMB is the faint, uniform glow of heat that fills the universe and is left over from the Big Bang itself. It was discovered unexpectedly in 1965 by Arno Penzias and Robert Wilson. The temperature of this radiation is about 2.7 degrees Kelvin, just a few degrees above absolute zero, making it incredibly cold by everyday standards. What makes the CMB so significant is what it represents: a snapshot of the universe when it was roughly 380,000 years old, long after the initial explosion. At this stage, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms in a process called recombination. This allowed photons, particles of light, to break free from matter and travel through space without constant scattering. Essentially, the CMB is the afterglow of that moment, giving astronomers a rare glimpse into the conditions and composition of the universe's earliest times. This radiation carries with it detailed information about tiny variations in temperature and density that existed just after the Big Bang. By studying these slight differences across the CMB, scientists can infer how matter was distributed in the early universe. These initial fluctuations acted as the seeds that eventually grew into the galaxies and massive cosmic structures we observe today. Missions like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have gathered detailed observations of the CMB. Thanks to their data, our understanding of the universe's composition, how much dark matter, dark energy, and ordinary matter it contains, has improved dramatically. The CMB also serves as a crucial testing ground for cosmological models. By comparing predictions from theory with what is actually observed, scientists refine their knowledge of the universe's history, how it has evolved, and what might lie ahead. Far from just a leftover echo of the Big Bang, the cosmic microwave background radiation offers a vital window into the history and workings of the universe itself. Alongside this, the theory of inflation proposes that the universe experienced an incredibly rapid expansion in the very first moments after the Big Bang. Specifically, from around 10 to the power of negative 36 seconds to about 10 to the power of negative 32 seconds after the event, the universe ballooned from sizes smaller than subatomic particles to far beyond what we can observe today, all in just a fraction of a second. This sudden expansion explains several key observations that the classical Big Bang theory struggles to address, such as why the universe appears so uniform and flat on large scales. This inflationary period stretched the fabric of space-time, smoothing out irregularities and setting the stage for the universe as we know it. Without it, many features of the cosmos would remain mysterious. Today, the combination of observational data and theoretical models of inflation continues to deepen our understanding of the origins, structure, and ultimate fate of everything around us. One of the most remarkable breakthroughs of inflationary theory lies in its ability to explain the incredible uniformity of the cosmic microwave background radiation, or CMB. Imagine the universe in its earliest moments, expanding at an unimaginable speed. During this rapid inflation, vast regions of space that today appear separated by immense distances were once closely connected in a way that allowed information and energy to flow between them. This causal connection during the inflationary period led to a nearly uniform temperature throughout the early universe. This uniformity is not just a curious detail, it is fundamental to understanding why the CMB shows only tiny fluctuations in temperature, subtle variations that hold the key to how the cosmos evolved from a smooth expanse into a richly structured tapestry of galaxies and clusters. Inflation also sheds light on another profound mystery: the flatness of the universe. Before inflation, the universe could have had any shape, curved like a sphere or saddle, or even twisted in more exotic ways. However, as the universe underwent exponential expansion, this process stretched out any initial curvature, like leaving behind a geometry that is astonishingly close to flat. This remarkable outcome solves what cosmologists call the flatness problem, a puzzle about why our observable universe seems so precisely balanced between collapsing back on itself and expanding forever. Thanks to inflation, the cosmos can be described as homogeneous and isotropic, uniform in all directions and locations. But inflation's story does not end there. It also plays a crucial role in the formation of the large-scale structures we see today. During the universe's explosive growth, tiny quantum fluctuations, minute irregularities in the energy density, were dramatically stretched across cosmic scales. These fluctuations created regions with slightly different densities, which, over billions of years, became the seeds for gravity to pull matter together. From these seeds emerged the cosmic web, a vast network of galaxies, clusters, and voids that defines the universe's large-scale structure. Together, these insights make inflation a cornerstone of modern cosmology. It weaves together explanations for a range of observations and fits seamlessly into the larger Big Bang framework, enriching our understanding of the universe's origin and evolution. Yet, despite these triumphs, our grasp of the universe remains incomplete. The Big Bang Theory and inflation do not fully describe what happened at the very beginning, at the singularity where densities and temperatures were so extreme that our current physics breaks down. The laws of general relativity and quantum mechanics, pillars of modern science, cannot yet be reconciled under these conditions. This limitation has driven scientists to search for a theory of quantum gravity, a unified framework that could explain the universe at its birth. Another profound challenge lies in the mysterious nature of dark matter and dark energy. Together, these invisible components make up about 95% of the universe's total energy content, yet their true identities remain unknown. Their presence is inferred only through gravitational effects and the universe's accelerated expansion, phenomena the Big Bang Theory alone does not fully address. Understanding dark matter and dark energy is crucial for unlocking deeper secrets about the cosmos, including how galaxies form and how the universe's expansion will unfold. Moreover, questions linger about the tiny temperature variations seen in the cosmic microwave background. Inflation offers a powerful explanation for the overall uniformity, but the detailed patterns of these fluctuations and how exactly they translate into the universe's vast structure are still the subject of ongoing research and debate. In this way, cosmology stands at the frontier of knowledge, balancing between remarkable discoveries and profound mysteries. Inflationary theory has propelled us forward, but it also points to the vast unknowns that remain as scientists continue to unravel the universe's deepest secrets. Finally, the landscape of cosmology is not without its challenges. While the Big Bang Theory stands as the leading explanation for the origins of the universe, it is far from the only contender. Alternative models, such as cyclic universes that endlessly repeat or multiverse theories suggesting countless parallel realities, push scientists to question and refine our understanding. These competing ideas highlight the limitations in our current knowledge and underscore the urgent need for more experimental evidence. As our telescopes become more powerful and our theoretical tools more sophisticated, new discoveries will inevitably reshape how we perceive the birth and evolution of everything around us. At the heart of all cosmic matter lie fundamental particles, the building blocks of the universe. These particles fall into two main groups, fermions and bosons. Fermions are the essential constituents of matter itself, with quarks and leptons taking center stage within this category. Quarks are the fundamental ingredients of protons and neutrons, which together form the nuclei of atoms. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom, each playing a unique role in the subatomic world. For instance, protons consist of 2 up quarks and 1 down quark, while neutrons are made of 2 down quarks and 1 up quark. Importantly, quarks never exist alone. They are permanently bound together by the strong nuclear force, carried by particles called gluons. Gluons act like an invisible glue, holding quarks tightly inside protons and neutrons. Leptons, the other major family of fundamental particles, include the well-known electron, which orbits the atomic nucleus. Electrons carry a negative electric charge and are vital for the chemical bonds that create the diverse matter we see every day. Beyond electrons, there are 5 other types of leptons, along with their elusive neutrino partners, muon neutrinos and tau neutrinos among them. Neutrinos are incredibly lightweight and interact so weakly with matter that trillions pass through your body each second unnoticed. These ghostly particles are born in powerful cosmic processes, such as nuclear fusion in stars and certain types of particle decay. Together, quarks and leptons make up all the ordinary matter in the universe. These particles are governed by fundamental forces: electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. Each force shapes how particles behave, interact, and bind together to create the fabric of reality. Understanding these particles and forces is key to unlocking the mysteries of matter, energy, and the very structure of our cosmos. In the universe's infancy, moments after the Big Bang, conditions were unimaginably extreme. The cosmos was a dense, searing plasma, brimming with energy so intense that particles continuously formed and vanished. During this blazing era, quarks and leptons emerged in a rapid-fire sequence driven by the universe's relentless expansion and cooling. Within microseconds, the energy allowed quarks to materialize from more fundamental entities. According to quantum chromodynamics, the theory describing the strong interaction, quarks are produced only in pairs or triplets. As the universe cooled, these quarks combined through the strong nuclear force to form protons and neutrons, the seeds of matter. Leptons, including electrons, also appeared in this fiery environment. Processes like pair creation, where energy transforms into particle-antiparticle pairs, allowed photons, particles of light, to spawn electron-positron pairs. Positrons, the antimatter counterparts of electrons, exemplify the deep symmetry woven into the laws of particle physics. As the universe continued to expand and cool over the first few minutes, a crucial process called Big Bang nucleosynthesis took place. Protons and neutrons fused to form the nuclei of the lightest elements, such as helium, deuterium, and lithium. Eventually, temperatures and densities fell low enough to permit the stable assembly of matter as we know it. In sum, the earliest moments of the universe were governed by extraordinary energy, rapidly shifting temperatures, and the dance of fundamental forces. Through these primordial conditions, quarks and leptons came into being, setting the stage for the formation of all matter that fills the cosmos today. This unfolding story continues to inspire scientists as they piece together the universe's grand origins and ultimate fate. The Higgs boson is one of the most fascinating and essential particles in the world of physics. It is an elementary particle linked to the Higgs field, an invisible energy field that fills the entire universe. This field is not something we can see or touch, but its presence is fundamental because it explains why other fundamental particles, such as protons and electrons, have mass. Without mass, these particles would not form the matter that builds stars, planets, and ultimately life itself. The key process behind this is called spontaneous symmetry breaking. Imagine particles moving through the Higgs field like a person wading through thick mud. As they travel through this invisible field, they interact with it and gain mass. This interaction slows the particles down, allowing them to have the weight necessary to form everything around us. It is this mechanism that shapes the fabric of the universe in ways that are both profound and subtle. The story of the Higgs boson took a monumental turn in 2012 when it was discovered at the Large Hadron Collider, LHC, a colossal machine built to explore the tiniest building blocks of nature. This discovery was a triumph, confirming a crucial part of the standard model of particle physics, the theory that describes the fundamental particles and forces that govern the universe. Scientists had theorized the Higgs boson's existence for decades, but detecting it required some of the most advanced technology ever created. The significance of the Higgs boson goes far beyond simply filling a gap in our understanding. By studying its properties, researchers hope to unlock mysteries that go deeper into the cosmos. For example, the Higgs field might hold clues about dark matter, a mysterious substance that makes up most of the universe's mass but cannot be seen directly. It may also shed light on why the universe contains more matter than antimatter, a profound question that has puzzled scientists for years. Understanding the Higgs boson is not just about particle physics. It could revolutionize how we understand the entire cosmos. The discovery itself is a testament to human curiosity and collaboration. Scientists from around the world worked together, pushing the boundaries of knowledge and technology. Their success shows how fundamental research can lead to new technologies, inspire future generations, and deepen our quest to understand the universe. Particle accelerators like the Large Hadron Collider are marvels of modern science. These machines accelerate charged particles, such as protons and electrons, to speeds close to the speed of light before smashing them together or into fixed targets. These high-energy collisions recreate conditions similar to those just after the Big Bang, allowing scientists to observe how particles form and interact. When particles collide at such incredible speeds, energy can transform into mass, creating new particles, just as Einstein's famous equation describes. This process is vital for discovering elusive particles like the Higgs boson. Surrounding the collision points are sophisticated detectors that capture the particles produced. Advanced technology analyzes this data to reconstruct the events, measuring properties such as mass, charge, and decay patterns. These measurements help scientists test and refine their theories about the universe's fundamental forces and components. Sometimes the findings confirm existing models, and other times they open the door to new ideas and discoveries. Beyond their role in discovery, particle accelerators foster international cooperation. Physicists from different countries and backgrounds come together to solve some of science's deepest mysteries. The technology developed for these accelerators often finds unexpected uses in other fields, such as medical imaging and material science, demonstrating the broad impact of this research. Another intriguing topic connected to particle physics is antimatter. Antimatter consists of particles that mirror ordinary matter particles, but carry opposite charges and certain properties. For example, the antimatter counterpart of the electron is the positron, which carries a positive charge instead of a negative one. When matter and antimatter meet, they annihilate each other, releasing energy in the form of gamma rays. Although antimatter exists naturally in tiny amounts and can be produced in laboratories, the universe we observe is overwhelmingly made of matter. This imbalance raises one of the biggest puzzles in cosmology and particle physics. Right after the Big Bang, it is believed that matter and antimatter were created in equal amounts. However, as the universe expanded and cooled, a subtle imbalance emerged, leaving more matter than antimatter. Why this happened is still not fully understood because the known laws of physics do not predict such a preference. Several theories attempt to explain this matter-antimatter asymmetry. One idea involves the violation of a principle known as charge parity symmetry during certain particle decay processes. Such violations could have tipped the scales in favor of matter, leading to the universe as we know it today. Solving this mystery could reshape our understanding of the origins of everything around us. In summary, the Higgs boson and related discoveries open a window into the smallest scales of nature, connecting us to the very beginnings of the universe. Through relentless scientific effort, human beings continue to push the frontiers of knowledge, striving to comprehend the unseen forces that shape reality itself. Additionally, some researchers are investigating the possibility of unknown interactions at extremely high energies that distinguish matter from antimatter. This line of inquiry hints at new physics beyond the current framework known as the Standard Model. Understanding why our universe is overwhelmingly composed of matter rather than antimatter could unlock profound insights into the fundamental laws governing everything around us. Solving this cosmic mystery may reveal entirely new particles, forces, or principles that science has yet to discover. Such breakthroughs would deepen our comprehension not only of the universe's origins, but also of its ultimate destiny. Exploring the nature of antimatter and how it relates to matter could radically transform our perspective on the cosmos and our place within it. The earliest atoms took shape during a crucial period called recombination, which occurred roughly 38,000 years after the Big Bang. Before this, the universe existed as a hot, dense plasma, a chaotic soup of protons, neutrons, and electrons moving at incredible speeds. In this intense environment, collisions between particles happened so frequently and with so much energy that stable atoms could not form. As the universe expanded, it cooled down. This cooling allowed particles to lose energy and finally come together to form the first neutral hydrogen atoms. This moment marked a turning point. At around 3,000 degrees Celsius, protons and electrons combined in the process we call recombination. Negatively charged electrons were captured by positively charged protons, causing a sharp decline in the number of free electrons floating in space. This transition allowed photons, or light particles, to travel freely for the first time, creating what we now observe as the cosmic microwave background radiation. This faint glow serves as a direct remnant from those early days, providing strong evidence of the universe's hot and dense beginnings. Hydrogen atoms made up the majority of the matter created at this stage, but helium also played a vital role. Helium formed during the first few minutes of the universe's existence through a process called Big Bang nucleosynthesis. During this brief but intense period, protons and neutrons fused to create helium nuclei. As a result, the universe was composed mainly of hydrogen and helium, elements that would become the building blocks of stars and galaxies. From clouds of gas composed primarily of these first atoms, stars eventually emerged. Within these stars, nuclear fusion processes forged heavier elements over millions of years. This cycle of star formation, evolution, and explosive deaths known as supernovae laid down the foundation for the rich variety of elements necessary for forming planets and, ultimately, life itself. The journey from the earliest atoms to the complex elements that make up everything we see around us is a testament to the dynamic and ongoing evolution of the universe. Primordial nucleosynthesis, which refers to the formation of light elements in the first few minutes following the Big Bang, took place roughly between 3 and 20 minutes after the universe began. During this fleeting period, conditions were incredibly hot and dense, enabling nuclear reactions among protons, neutrons, and other particles. Initially, the universe consisted mostly of free protons and neutrons. As temperatures dropped to levels suitable for nuclear interactions, these particles began to fuse. The most significant nuclear reaction was the creation of helium from hydrogen. This process started with the fusion of 2 protons to form a deuterium nucleus, an isotope of hydrogen made of 1 proton and 1 neutron. Subsequently, deuterium nuclei combined with additional protons and neutrons, building up helium nuclei. By the end of primordial nucleosynthesis, it is estimated that approximately 75% of the universe's normal matter had become hydrogen, around 25% had converted into helium, and trace amounts had formed lithium and beryllium. These light elements formed the essential building blocks for the stars and galaxies that appeared much later in cosmic history. Remarkably, the relative abundances of these elements, as predicted by primordial nucleosynthesis theory, match closely with what astronomers observe today. This consistency confirms the accuracy of our understanding of the universe's earliest moments and continues to guide researchers as they unravel the mysteries of our cosmic origins. The significance of primordial nucleosynthesis is truly monumental. It provides a vital window into the earliest moments of our universe, revealing the physical conditions that shaped everything that followed. This process, unfolding within the first few minutes after the Big Bang, set the cosmic stage for the formation of all matter we know today. It is the cornerstone for the creation of simple elements that later became the building blocks for stars, planets, and ultimately, life itself. In the moments just after the Big Bang, the universe was an unimaginably hot, dense sea of elementary particles, protons, neutrons, and electrons moving in a chaotic, energetic dance. As the universe expanded, it cooled rapidly. This cooling was crucial, allowing protons and neutrons to combine and form the first atomic nuclei in a process known as primordial nucleosynthesis. These nuclear reactions happened in a very narrow window, roughly between 3 and 20 minutes after the universe began expanding. Hydrogen, with its single proton, emerged as the most abundant element, making up about 75% of the normal matter created. Neutrons, though less plentiful, played a critical role by combining with protons to form deuterium, a heavier isotope of hydrogen. Deuterium nuclei then fused further to create helium nuclei, each consisting of 2 protons and 2 neutrons. The strong nuclear force, the fundamental force that binds protons and neutrons inside atomic nuclei, drove these fusion processes. Helium's formation was favored because it creates a more stable configuration compared to the individual protons and neutrons floating freely in space. By the end of this early fusion period, nearly a quarter of the universe's ordinary matter had become helium. Only trace amounts of other light elements like lithium and beryllium were produced. These elements required more energy to form, making their creation during primordial nucleosynthesis far less common. This elemental makeup, primarily hydrogen and helium, would profoundly influence the universe's evolution in the billions of years to come. The dominance of these light elements was essential for the birth and life cycle of stars. Hydrogen and helium acted as the fuel that powered stellar nucleosynthesis, the process by which stars forge heavier elements like carbon, oxygen, and iron deep within their cores. Over cosmic time, these heavier elements would seed new generations of stars, planets, and eventually life. Approximately 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with these nuclei in a phase called recombination. This event created neutral atoms, allowing photons, particles of light, to travel freely for the first time. The release of this light is what we now detect as the cosmic microwave background radiation, a faint glow that permeates the entire universe and serves as a snapshot of this critical moment in cosmic history. While the visible matter in the universe tells a compelling story, the invisible force known as dark matter played an equally important, if indirect, role. Dark matter does not emit, absorb, or reflect light, making it undetectable by ordinary means. Yet its gravitational influence is essential. Dark matter, thought to make up about 26% of the universe's mass energy content, created gravitational wells that pulled ordinary matter together. These wells helped form clumps of gas and dust, which would eventually collapse under gravity to form the first stars and galaxies. Without dark matter's gravitational scaffolding, the universe might have remained a diffuse, featureless expanse, unable to develop the complex structures we observe today. In this way, primordial nucleosynthesis and dark matter together shaped the cosmic landscape. From the fiery birth of the first atomic nuclei to the formation of the earliest stars and galaxies, these processes underpin the story of how the universe transformed from a hot, dense particle soup into the vast, richly structured cosmos we inhabit. Understanding this chain of events not only sheds light on the origins of matter, but also reveals the profound interconnectedness of forces and particles at the dawn of time, reminding us that the story of the universe is one of constant transformation, governed by both the known and the mysterious. While dark matter does not directly shape the creation of elements, its invisible grip through gravity is essential to the cosmic dance that leads to star formation. These stars become the cosmic forges where heavier elements are born. By understanding dark matter's role, we gain a vital perspective on the grand story of the universe's evolution and the origins of the very elements that make up galaxies, solar systems, and life itself. To unravel how the universe's first molecules came into being, we must travel back nearly 14 billion years to the aftermath of the Big Bang. At this dawn of time, the universe was an unimaginably hot and dense environment, with temperatures soaring into the millions of degrees. This intense energy prevented stable atoms from forming. Instead, the cosmos was a seething sea of fundamental particles like quarks, continuously appearing and disappearing as the universe expanded and cooled. About 378,000 years after the Big Bang, a pivotal moment known as recombination took place. Electrons and protons finally combined to form neutral hydrogen atoms. This event turned the universe transparent, allowing light to travel freely through space for the first time. But hydrogen, the simplest atom, was only the beginning. Driven by gravity, clouds of hydrogen atoms began to gather, eventually giving rise to the first stars and galaxies. Inside these primordial stars, nuclear fusion sparked to life, forging helium and small amounts of light elements such as lithium and beryllium. As these stars aged and died, they exploded in spectacular supernovae, dispersing their enriched material, mostly hydrogen and helium, throughout the cosmos. It was in the aftermath of these cosmic cataclysms that more complex molecules started to form, creating the earliest molecular compounds. This process laid the groundwork for the formation of stars, planets, and molecules we recognize today, such as water and carbon dioxide. The emergence of these first molecules was a monumental milestone in the universe's chemical evolution. It marked the beginning of complexity, setting the stage for the vast diversity of matter that eventually led to life. These early molecules connected the simplest building blocks of matter to the intricate web of existence that surrounds us. Interstellar dust, tiny particles composed mainly of carbon, silicate minerals, and ice, plays a surprisingly critical role in this story. Though it constitutes only a tiny fraction of the universe's mass, this dust fills the space between stars and acts as a crucial catalyst in the formation of complex molecules. As stars and galaxies formed from primordial hydrogen and helium, heavier elements were synthesized in stellar cores and later expelled during stellar deaths. The interstellar medium, enriched with these elements, became a fertile environment where dust grains provided surfaces for atoms and molecules to stick, collide, and react. This cosmic chemistry gave rise to increasingly complex molecules, including the simplest organic compounds like amino acids, which are fundamental to life. Observations of dense molecular clouds rich in dust have revealed an abundance of these organic molecules, suggesting that the building blocks of life may have formed far from Earth in the cold, dark reaches of space. The surfaces of interstellar dust grains enable these complex molecules to assemble and grow into larger structures, bridging the gap between simple chemistry and biology. The journey from hydrogen atoms to complex molecules is a remarkable saga of transformation. The combined forces of stellar evolution and the subtle influence of interstellar dust weave a tale of cosmic creativity. This transformation enriches galaxies with chemical diversity and sets the stage for the emergence of life. It reminds us that the fundamental components of existence often arise in the quiet, shadowy spaces between the stars. Detecting complex molecules in space is one of the most thrilling scientific quests of our time, blending cutting-edge technology with the vastness of the cosmos. Scientists use a range of sophisticated techniques to uncover these molecular mysteries, each method capitalizing on the unique ways molecules interact with light across the electromagnetic spectrum. At the heart of this pursuit is spectroscopy, a powerful technique that breaks down light into its constituent colors to reveal hidden information. When light travels through or bounces off clouds of gas and dust in space, molecules within these clouds absorb or emit light at very precise wavelengths. These interactions produce distinct spectral patterns known as absorption or emission lines, which act as molecular fingerprints. By decoding these fingerprints, astronomers can identify the presence of specific molecules like water, carbon dioxide, and a variety of organic compounds. These findings have been made in diverse environments, ranging from interstellar clouds to the atmospheres of distant exoplanets. In addition to visible and infrared spectroscopy, radio telescopes play a vital role. Many complex molecules emit signals in the radio wavelength when they transition between energy states. Detecting these radio emissions allows scientists to probe the physical and chemical conditions of celestial regions with incredible precision. A notable example is methanol, an organic molecule frequently found in dense clouds between stars. The ability to capture such signals opens a window into the hidden chemical landscapes of space. Thanks to powerful instruments like the Atacama Large Millimeter Submillimeter Array and the James Webb Space Telescope, our capacity to detect and analyze complex molecules has grown dramatically. These observatories scan the universe with unprecedented sensitivity, revealing not just familiar molecules, but also exotic compounds that challenge and enrich our understanding of cosmic chemistry. Each discovery deepens our knowledge of the molecular tapestry woven throughout the universe and nudges us closer to unraveling the origins of life itself. Interstellar space is surprisingly rich in complex molecules. some of which play critical roles in cosmic chemical evolution. One particularly intriguing class is polycyclic aromatic hydrocarbons, organic molecules made of several fused benzene rings. These form under intense energy conditions generated by stellar activity, hinting at sophisticated chemistry taking place even in the cold depths of space. Their widespread presence suggests that life's fundamental chemical building blocks might be far more common than previously imagined. Even more compelling is the discovery of amino acids, the essential components of proteins. Scientists have identified specific amino acids within meteorites and molecular clouds scattered across the galaxy. Glycine, the simplest amino acid, has been found in the dense molecular cloud Sagittarius B2. This discovery fuels the exciting possibility that the raw materials for life are distributed throughout the cosmos, potentially leading to life-bearing environments beyond Earth. Sugars and alcohols also emerge in this cosmic chemistry saga. Complex sugars like ribose, a vital part of RNA, have been detected in comet samples and interstellar gas clouds. Meanwhile, molecules such as ethyl alcohol further illustrate the organic diversity thriving in space. These findings not only broaden our view of molecular complexity, but also outline potential pathways for how life's essential substances might assemble in the universe. The detection of these molecules paints a picture of a universe bustling with chemistry, bridging the gap between stellar phenomena and the biological processes that could give rise to life. As astronomers continue to explore the depths of space, they reveal intricate connections between the elements forged in stars and the organic compounds that might one day explain the origin of life on Earth and beyond. The journey of organic molecule formation in the cosmos begins shortly after the Big Bang. As the universe cooled, primordial hydrogen and helium atoms started to gather, creating the simplest matter. Over billions of years, gravity pulled these particles together to form stars, which act as cosmic forges. Through nuclear fusion, stars generate heavier elements that enrich the universe's chemical diversity, setting the stage for the formation of complex molecules essential for life. In this grand cosmic narrative, detecting complex molecules is more than a scientific achievement. It is a voyage into understanding the very essence of life's potential, revealing how the universe is not just a vast emptiness, but a dynamic laboratory where the ingredients of life are mixed, assembled, and scattered across the stars. Inside the blazing cores of stars, an incredible process called nuclear fusion takes place. This is where hydrogen atoms merge to form helium, releasing immense energy in the process. But fusion does not stop there. As stars age, they fuse helium into heavier elements like carbon, nitrogen, and oxygen, creating the very building blocks that life on Earth depends on. When stars reach the end of their life cycles, they explode in spectacular supernovae or blow strong stellar winds, scattering these elements far and wide into the surrounding cosmic space. This scattered material, enriched cosmic dust and gas, collects in dense, cold molecular clouds where new chemical adventures begin. Within these vast clouds, simple molecules such as carbon dioxide, ammonia, and water start to combine, slowly assembling more complex organic compounds. Many of these reactions happen on the tiny surfaces of interstellar dust grains, which act like natural laboratories or catalysts, encouraging atoms and molecules to interact in ways that form amino acids, nucleobases, and sugars. These molecules are essential ingredients for life as we know it. The chemistry within these clouds is further energized by cosmic rays and ultraviolet radiation, which provide the necessary push to drive complex reactions forward. As comets and asteroids form within these environments, they trap and carry these organic molecules across space. When these icy travelers eventually collide with planets, they may deliver the crucial ingredients for life, possibly igniting the early chemical processes that gave rise to living organisms on worlds like Earth. Across the vast reaches of the universe, a special class of organic molecules known as polycyclic aromatic hydrocarbons, or PAHs, plays a key role in cosmic chemistry and our quest to understand life beyond Earth. These complex molecules made up of multiple fused benzene rings are surprisingly abundant in interstellar space. They serve as reservoirs of carbon, a vital element in creating complex organic compounds, and their presence in dense molecular clouds highlights their importance in ongoing chemical evolution. PAHs influence star formation too. As stars emerge from these clouds, the molecules affect the surrounding environment by participating in radiative processes that shape the birth of new molecules. This interaction adds another layer to the rich tapestry of chemistry in space. Even more fascinating is the potential link between PAHs and the origins of life. Their molecular structure allows them to take part in reactions that could lead to biologically important molecules. Some research suggests that PAHs might be precursors to amino acids and other large organic molecules crucial for life. Finding these molecules in the remnants of ancient stars and galaxies hints at a universal story. From the hearts of stars to the building blocks of life, complex chemistry may be the bridge that connects cosmic evolution to living worlds. Moreover, detecting pH levels in the atmospheres of distant exoplanets opens a remarkable window into the chemical dynamics far beyond our solar system. This discovery goes beyond simple observation. Identifying pH can act as a critical signpost of organic chemistry unfolding on alien worlds. Such findings push us to confront profound questions about whether these environments might support life as we know it, or even forms of life we have yet to imagine. One of the key players in this cosmic narrative is a class of molecules known as polycyclic aromatic hydrocarbons, or PAHs. These complex compounds are much more than mere cosmic markers. They could represent a vital bridge linking the simplest molecules maze in space to the elaborate chemistry necessary for life's emergence. PAHs inhabit molecular clouds, dense, chilly regions packed with gas and dust, primarily hydrogen molecules, but also a rich mix of other elements and compounds. These clouds serve as cosmic laboratories where chemistry unfolds on a grand scale. Molecular clouds are far more than space dust. They are the cradles of chemical evolution. Within their dense environments, a symphony of reactions takes place, enabling simple molecules to join forces and create intricate organic compounds. Amino acids, sugars, and other essential building blocks of life have been detected within these clouds, suggesting that the ingredients for life might be spread widely throughout the universe. The story of molecular clouds intertwines with the birth and death of stars. When gravity causes a portion of a molecular cloud to collapse, it ignites a chain reaction of chemical and physical changes. Inside these newborn stars, the intense heat and crushing pressure spark nuclear fusion, a process that forges heavier elements from lighter ones. These stars eventually meet dramatic ends as supernova, exploding spectacularly and scattering elements like carbon, oxygen, and nitrogen into space. This stellar debris mixes with existing molecular clouds, enriching their chemical composition and enabling the creation of even more complex molecules. This cycle of star birth and death creates a cosmic rhythm, constantly reshaping the chemical makeup of galaxies and seeding future generations of stars and planets. The chemical interplay in molecular clouds is not just a backdrop, but a fundamental force driving the universe's ongoing evolution, connecting phases of stellar life and shaping the environments where new stars and planets will emerge. Looking even further back, the formation of the very first stars happened just a few 100 million years after the Big Bang, during a phase known as the Cosmic Dawn, or Era of Reionization. At this time, the universe was dominated by hydrogen and helium, the simplest elements, while dark matter's mysterious gravity sculpted the large-scale structure of the cosmos. Dark matter, invisible yet massively influential, created gravitational wells that pulled in primordial gas. As this hydrogen and helium-rich gas fell into these wells, it grew denser and hotter, eventually collapsing into protostars. As these clouds contracted under gravity, their cores reached temperatures of about 10 million degrees Celsius, triggering nuclear fusion, the process that transforms hydrogen into helium and powers stars. These first stars, called Population 3 stars, were vastly different from the stars we see today. They were much larger, hotter, and composed almost entirely of hydrogen and helium, lacking the heavier elements produced by later stellar generations. Their formation marked a turning point in cosmic history. When these massive stars ended their lives in violent supernova explosions, they spread newly forged elements across the cosmos, enriching the interstellar medium and laying the foundation for the complex chemical environments we observe today. This cycle of star formation and destruction has been the engine driving the chemical richness of the universe, leading to the diverse array of stars, planets, and potentially habitable worlds that astronomers continue to discover. The story of molecular clouds, star birth, and cosmic chemistry is not just about distant objects in space. It is the epic tale of how the universe builds complexity, setting the stage for life itself. And so, the story of the very first stars in the universe begins with the enigmatic population 3 stars. These ancient giants stand apart from all the stars that followed, not only because of when they formed, but also due to their extraordinary nature. Born from clouds of primordial gas almost entirely made up of hydrogen and helium, population 3 stars were the pioneers in the cosmic landscape, shaping the universe's early evolution in profound ways. These stars were colossal. Imagine suns hundreds of times more massive than our own, blazing with unimaginable power. Their enormous size meant they burned their nuclear fuel incredibly fast, living brief, intense lives measured in just a few million years. A blink of an eye compared to the billions of years that many modern stars can endure. The furnace at their cores was a site of extreme fusion, turning hydrogen into helium with ferocious energy output, flooding the early cosmos with radiation that helped transform its very fabric. Perhaps the most remarkable feature of these stars was their pristine composition. They formed before any heavier elements existed, crafted only from the simplest building blocks left over from the Big Bang. Without metals or other complex elements, these stars were chemically pure. But as their short lives ended in spectacular supernova explosions, they forged the first heavier elements like carbon, oxygen, and nitrogen. These elements then spread into space, seeding the cosmic environment and enabling future generations of stars, planets, and eventually life to arise. The birthplaces of population 3 stars were mysterious and dark, hidden within regions dominated by invisible dark matter. This dark matter, though unseen, wielded gravity like a cosmic architect, gathering gas and dust into dense clouds where these first stars could ignite. The immense energy radiated by these stars altered their surroundings drastically, heating and ionizing the gas around them. This process played a vital role in what scientists call the cosmic reionization era, a transformational period that reshaped the early universe's structure. Understanding these first stars is just one part of the grand quest to uncover the universe's origins. Astronomers face a daunting challenge in studying the earliest galaxies, which are faint and distant relics of a long-lost past. Because the universe is constantly expanding, light from those ancient galaxies is stretched from its original ultraviolet glow into the infrared spectrum by the time it reaches us. Powerful instruments like the Hubble Space Telescope and the more recent James Webb Space Telescope, with their advanced infrared capabilities, have opened new windows onto this early era, allowing scientists to peer back billions of years. Another remarkable tool in this cosmic investigation is gravitational lensing. When a massive galaxy or cluster lies between us and a distant galaxy, its gravity bends and magnifies the light from the farther object, like a natural cosmic telescope. This effect reveals faint galaxies that would otherwise remain invisible, giving astronomers precious glimpses into the universe's infancy. Beyond observations, theoretical models and computer simulations are essential. By recreating galaxy formation under various physical conditions, these simulations help interpret what telescopes see and predict features of early galaxies that remain hidden. This combination of observation and theory brings us closer to understanding how galaxies, stars, and the cosmic structures we know today first took shape. Speaking of cosmic structures, the cosmic web is an astonishing, vast network that maps the universe on the largest scales. It's a grand tapestry woven from countless galaxies, galaxy clusters, and dark matter filaments, thread-like structures connecting dense regions of space, separated by vast voids where matter is sparse. This web is the backbone of cosmic architecture, governing how matter is spread and how galaxies grow and evolve. The origins of the cosmic web trace back to the first moments after the Big Bang, when the universe was nearly uniform but contained tiny quantum fluctuations in density. Over billions of years, these slight differences grew under the pull of gravity, especially influenced by dark matter, which acts as a cosmic scaffold invisible to our eyes, but essential for gathering ordinary matter. As matter clumped together, the first stars, clusters, and galaxies formed. These small structures merged and grew, sculpting the complex web of filaments and voids we observe today. In essence, the story of population 3 stars, early galaxies, and the cosmic web is a tale of transformation, from simplicity to complexity, from a hot, dense beginning to a rich, structured cosmos filled with wonders. Each discovery, whether through telescopes or simulations, peels back another layer of this vast history, deepening our understanding of the universe's earliest chapters and the origins of everything we see around us. The cosmic web acts as the universe's grand architecture, an intricate framework that astronomers rely on to unravel the mysteries of galaxy distribution and the flow of cosmic matter. This vast network, made up of filaments stretching across unimaginable distances, connects galaxies in a cosmic tapestry that tells the story of the universe's earliest days and its continuous evolution. Observations of this web allow scientists to peer back in time, tracing how galaxies formed and evolved from the primordial soup of the early cosmos. Large-scale survey projects, like the Sloan Digital Sky Survey, have been instrumental in mapping this cosmic web with unprecedented detail. By cataloging the positions and movements of millions of galaxies, these surveys help researchers build a dynamic picture of the web's structure and how it has changed over billions of years. Understanding the cosmic web is not just about knowing where galaxies are, it is about uncovering the physical processes that govern the universe on its grandest scales. At the heart of many galaxies lie supermassive black holes, enigmatic giants with masses ranging from millions to billions of times that of our sun. These black holes are not mere cosmic curiosities, but key players in the story of galaxy formation and evolution. Most large galaxies, including our own Milky Way, harbor these gravitational behemoths at their centers. The formation of these black holes appears to be tightly linked to the birth and growth of their host galaxies, influencing their structure and the rate at which new stars are born. The leading theory proposes that supermassive black holes originated either from the direct collapse of massive gas clouds in the early universe or from the merging of smaller black holes. As they formed and grew, their immense gravitational pull began shaping their surroundings. This influence extends to the movement of stars and gas within the galaxy, often resulting in the creation of a central bulge and regulating star formation. Supermassive black holes also release vast amounts of energy through feedback processes as they consume matter. This energy, emitted as radiation, can heat the surrounding gas and prevent it from cooling enough to form new stars. Such feedback mechanisms act as cosmic regulators, balancing the growth of the black hole with the galaxy's star-forming activity. In periods of intense activity, these black holes can produce quasars, phenomena so luminous that they can outshine entire galaxies. Statistical studies reveal a profound connection between the mass of a supermassive black hole and the properties of its host galaxy's bulge, suggesting a co-evolutionary dance. This relationship highlights how black holes and galaxies grow together, each influencing the other. Exploring this interplay offers invaluable insights into how galaxies are shaped, demonstrating that supermassive black holes are far from passive bystanders. They are active architects of cosmic history. Beyond the visible and gravitational actors lies dark energy, a mysterious force that dominates the universe's expansion. Since the Big Bang, the universe has been expanding, but the startling discovery that this expansion is accelerating changed everything. Dark energy, thought to make up about 70% of the universe's total energy, acts as a repulsive force that counteracts gravity's pull. Its exact nature remains one of the greatest puzzles in physics. As the universe expands, ordinary matter becomes less dense, yet dark energy's influence grows, driving the acceleration. This unseen force shapes the destiny of the cosmos on the largest scales, making it essential to our understanding of cosmic evolution. Together, the cosmic web, supermassive black holes, and dark energy form the pillars of modern cosmology. Their interconnected roles weave a complex narrative of structure, dynamics, and transformation, revealing a universe far more dynamic and mysterious than once imagined. However, dark energy presents one of the most profound mysteries in modern cosmology. Unlike matter, which thins out as the universe expands, dark energy seems to maintain a constant density throughout space. This means that as the universe grows larger and larger, dark energy's influence becomes more and more dominant. The direct consequence of this growing dominance is the observed accelerated expansion of the universe, a phenomenon that has puzzled scientists for decades. The idea of dark energy is closely tied to the cosmological constant, a concept introduced by Albert Einstein in his theory of general relativity. Einstein initially proposed this constant to allow for a static universe, as the prevailing belief at the time was that the cosmos neither expanded nor contracted. However, after Edwin Hubble's groundbreaking discovery that the universe is expanding, Einstein discarded the cosmological constant, calling it his biggest blunder. Yet, fast forward to the late 20th century, and scientists discovered that the universe's expansion is actually speeding up, not slowing down. This unexpected acceleration breathed new life into the cosmological constant as a possible explanation for dark energy. While the cosmological constant offers a simple and elegant model of dark energy as a constant energy density filling space, it is not the only theory. Alternative explanations have been proposed, including dynamic forms of dark energy such as quintessence, which vary over time and space. Understanding these possibilities is critical because the behavior of dark energy will determine the ultimate fate of the cosmos. If dark energy continues to dominate over the gravitational forces that pull matter together, it could drive galaxies farther and farther apart at ever-increasing speeds. In such a scenario, the universe would expand forever, growing colder and emptier, leading to what scientists call the Big Freeze. Celestial structures like galaxies and clusters might eventually become isolated islands in a vast, dark sea. This dramatic fate underscores why unraveling the true nature of dark energy remains a central challenge for cosmologists and theoretical physicists alike. Turning to the cosmic life cycle of stars, their story begins in massive clouds of gas and dust scattered throughout space. These enormous molecular clouds, primarily composed of hydrogen molecules mixed with other gases and tiny dust particles, create cold, dense pockets where the magic of star formation takes place. The birth of a star starts when a region within a molecular cloud experiences gravitational collapse. This can be triggered by various cosmic events, such as shockwaves from nearby supernova explosions or collisions between clouds themselves. As the gas and dust in this region compress under gravity, the density and temperature rise. At the heart of this collapsing material, a protostar forms, a dense core that gradually gathers more mass as surrounding matter falls inward. During this phase, the protostar often develops a rotating disk of gas and dust around it. This disk acts like a conveyor belt, funneling additional material onto the growing star. As the core temperature climbs to millions of degrees Celsius, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing vast amounts of energy in the process. When the energy output from these fusion reactions balances the inward pull of gravity, the protostar stabilizes and enters the main sequence phase, officially becoming a fully formed star. The surrounding disk, rich in leftover gas and dust, often gives rise to planets, moons, and other celestial bodies through similar gravitational processes. Thus, the formation of stars is not only a spectacular cosmic event, but also the foundation for creating entire planetary systems. In this way, stars shape the architecture of the universe and provide the essential conditions for life to emerge on worlds like our own. The universe tells its story through an intricate cosmic dance where gas, dust, and gravity come together to ignite the birth of stars. These brilliant lights do more than just illuminate the vast darkness. They forge the heavier elements essential for life itself and power the relentless march of cosmic evolution. At the heart of every star lies nuclear fusion, a process so powerful it fuels stars across the cosmos, including our very own sun. Deep within a star's core, unimaginable temperatures and crushing pressures create an environment where hydrogen nuclei, normally repelling each other, overcome their barriers and collide to fuse into helium. This fusion process releases a staggering amount of energy in the form of light and heat, making stars shine brightly for millions to billions of years. To sustain fusion, temperatures must soar to millions of degrees Celsius. At such extremes, electrons are stripped from atoms, leaving behind a searing plasma of free protons and nuclei. When these particles slam together with enough force, they fuse into heavier nuclei, releasing energy thanks to a remarkable phenomenon called the mass-energy equivalence principle. This principle means that a tiny fraction of the mass involved in these reactions transforms directly into energy, powering the star's brilliance. As stars age, they gradually consume their hydrogen fuel. Eventually, they begin fusing helium into heavier elements such as carbon and oxygen. This progression sets off a cascade of fusion reactions, producing elements all the way up to iron within massive stars. When fuel runs out, the star's core can no longer support its own weight, sometimes leading to breathtaking explosions known as supernovae. These violent events scatter the newly formed elements into space, seeding the cosmos with the building blocks for planets and life. Stars are elemental forgers, producing heavier atoms through a series of complex nuclear fusion processes throughout their lives. Early on, stars fuse hydrogen into helium at their cores. Once hydrogen runs low, the core contracts and heats up, enabling fusion of helium into heavier nuclei like carbon and oxygen. This phase generally occurs in stars that are several times the mass of our Sun, where core temperatures reach around 100 million degrees Celsius. A fascinating reaction occurs when 3 helium nuclei combine to form carbon, a process known as the triple alpha process. Carbon nuclei can then collide with other particles, fusing into heavier elements such as neon and magnesium. This stellar nucleosynthesis happens deep within the core and sometimes in surrounding layers, depending on the star's size. For the most massive stars, once iron accumulates in the core, fusion changes from an energy-releasing process to one that consumes energy. Iron cannot power fusion to hold up the star, causing the core to collapse under immense gravity. This collapse triggers a supernova explosion, releasing shock waves and spewing elements into the surrounding space. Supernovae environments are extreme and fascinating. Here, a rapid neutron capture process, called the R process, forges even heavier elements like gold and uranium. The debris from these explosions enriches the interstellar medium, from which new stars and planetary systems arise, continuing the cosmic cycle of element creation. When a star runs out of fuel, its fate depends largely on its mass. Smaller stars, similar to our Sun, begin to grow unstable as hydrogen in their cores is depleted. The core contracts while outer layers expand and cool, transforming the star into a red giant. During this phase, the star may briefly fuse helium into heavier elements before shedding its outer layers, which drift into space as a glowing nebula. The core that remains becomes a white dwarf, an incredibly dense, cooling remnant that will fade over billions of years. In stark contrast, massive stars experience a more violent fate. After exhausting their fuel through multiple fusion stages, their cores become iron-rich and unable to generate energy through fusion. The core collapses catastrophically, generating a supernova explosion that blasts the star's outer layers into the cosmos. Depending on the original star's mass, the core remnant becomes either a neutron star, an ultra-dense ball of neutrons, or a black hole, a region of space with gravity so intense that not even light can escape. This cosmic life cycle, driven by mass and fusion, shapes the universe dramatically. Massive stars end their lives in spectacular explosions, scattering the elements that form planets and even life itself, while smaller stars conclude their journey quietly, but no less fascinatingly. Supernovae play a crucial role in the evolution of the universe by distributing heavy elements far and wide. When a massive star explodes, it releases vast amounts of material into the interstellar medium, elements forged during the star's life and during the explosion itself, including precious metals like gold and radioactive elements like uranium. The tremendous energy of a supernova sends shockwaves rippling through nearby gas and dust clouds, compressing them and triggering the birth of new stars. These newborn stars inherit the enriched chemical mix spread by their explosive predecessors, creating a cosmic legacy of complexity and diversity. Through this ongoing cycle, the universe continually builds its elemental tapestry, from the simplest hydrogen atom to the richest heavy elements, all essential ingredients for the grand story of stars, planets, and life. Moreover, the explosive death of a star in a supernova sends shockwaves rippling through galaxies, dramatically altering their dynamics. This cosmic cataclysm injects vast amounts of energy and matter into the interstellar medium, the vast space filled with gas and dust between stars. The expelled material enriches this medium with heavy elements, seeding the birthplaces of new stars. In this way, supernovae act as powerful engines driving the evolution of galaxies, continuously shaping their structure and chemical makeup across billions of years. Additionally, supernovae are vital tools for astronomers trying to understand the cosmos itself. Observations of a particular type, called Type Ia supernovae, have revolutionized our grasp of cosmic distances and the universe's expansion. These explosions serve as standard candles, objects with known brightness that allow scientists to measure how far away they are with great precision. Through these measurements, researchers uncovered the surprising discovery that the universe's expansion is accelerating, a finding that has profound implications for the ultimate fate of everything we know. Thus, supernovae are far more than dazzling explosions. They are fundamental agents in the grand cycle of stellar birth, evolution, and death, weaving an intricate cosmic tapestry that shapes the universe's past, present, and future. Neutron stars, the dense leftovers of massive stars that have ended their lives in supernova explosions, represent some of the most extreme objects in the universe. When a star at least 8 times the mass of our Sun runs out of nuclear fuel, its core collapses in less than a second under gravity's immense pull. During this rapid implosion, protons and electrons merge to form neutrons, leaving behind a star composed almost entirely of these densely packed particles. The density of a neutron star defies imagination. Just a tiny cube of neutron star material the size of a sugar cube would weigh as much as all the people on Earth combined. This incredible density is held in check by quantum forces known as neutron degeneracy pressure, which arises because neutrons resist being squeezed into the same space. Neutron stars are astonishingly compact, typically about 10 kilometers in radius, yet they possess magnetic fields billions of times stronger than Earth's. Many spin rapidly, some rotating multiple times every second. If their magnetic axis is tilted relative to their rotation, they emit beams of radiation like cosmic lighthouses, appearing as pulsars to observers on Earth. These pulsars provide astronomers with precious data, helping unlock the secrets of matter under extreme conditions and the fundamental laws governing our universe. The formation of neutron stars plays a key role in the cosmic cycle, not only marking the final stage of massive star evolution, but also contributing to the creation of heavy elements through neutron capture during the supernova explosion. They form a bridge between ordinary stars and even more exotic objects like black holes, raising deep questions about the nature of matter and the fundamental forces at work in the universe. Turning now to the birth of planets, this process unfolds within protoplanetary disks, vast rotating disks of gas and dust encircling newborn stars. During the earliest stages of star formation, gravity pulls material from a surrounding molecular cloud into a dense core that ignites to form a star. The leftover gas and dust spread out into a flattened disk, serving as the raw material for planets to form. Within this swirling disk, tiny grains of dust and ice collide and stick together, gradually growing into larger clumps called planetesimals. This initial phase of growth can span several million years. Through countless collisions and mergers, planetesimals form even bigger bodies called protoplanets. These grow by pulling in more material via gravity and ongoing collisions, eventually becoming full-sized planets. Where a planet forms within the disk greatly influences its nature. Close to the star, where temperatures soar, only metals and rocky materials survive, giving rise to rocky planets like Earth and Mars. Farther out, in cooler regions, lighter gases like hydrogen and helium accumulate, forming massive gas giants such as Jupiter and Saturn. Here, compounds like ammonia and methane also join the mix. As the protoplanetary disk gradually thins out, due in part to radiation from the young star and other dynamic forces, the newly formed planets settle into stable orbits. Some may collide, while others get ejected from the system altogether. The survivors arrange themselves into the diverse planetary systems we observe throughout our galaxy today, each a unique outcome of this complex and wondrous cosmic dance, shaped by the extraordinary and unique conditions within their own protoplanetary disks and influenced by the complex dynamics of their formation. The story of how our solar system came to be is a tale as ancient as time itself. The prevailing theory that explains this cosmic birth is known as the nebular hypothesis. It proposes that around 4.5 billion years ago, our solar system emerged from the collapse of a massive molecular cloud, a swirling expanse of gas and dust, primarily composed of hydrogen and helium. This vast cloud, possibly disturbed by the shockwave of a nearby supernova or other dramatic cosmic events, began to collapse under its own gravity. As it contracted, it flattened into a spinning protoplanetary disk. At the center of this disk, the densest region formed what would become our Sun, igniting nuclear fusion and heralding the birth of a new star. Surrounding this newborn Sun, the remaining gas and dust spread out in a rotating disk, a fertile nursery where the planets would begin to take shape. Within this protoplanetary disk, tiny particles collided and stuck together through a process called collisional accumulation. Gradually, these particles grew into larger bodies known as planetesimals. Over millions of years, these planetesimals merged to form protoplanets. The temperature and pressure gradients across the disk played a critical role in shaping the kinds of planets that formed at different distances from the Sun. Closer in, where it was hotter, rocky planets like Earth and Mars took shape. Farther out in the cooler reaches, massive gas giants such as Jupiter and Saturn emerged, their strong gravity capturing vast amounts of hydrogen and helium. Even farther beyond Neptune, icy bodies coalesced, later becoming the dwarf planets and comets that continue to wander the solar system today. As the Sun's nuclear fusion roared to life, powerful radiation and solar winds swept away much of the remaining gas, effectively halting the planet formation process. This clearing left behind a structured solar system, with planets, moons, asteroids, and comets locked into their orbits, a cosmic dance choreographed by gravity and time. This nebular hypothesis has grown and evolved alongside advancements in astronomy and planetary science, deepening our understanding not just of our own solar history, but also of how planetary systems form throughout the universe. Beyond our solar system, the discovery of exoplanets, planets orbiting stars other than the Sun, has revolutionized our view of the cosmos. Since the first confirmed detection of an exoplanet in 1995, thousands more have been found, with their numbers increasing rapidly. Current estimates suggest that the Milky Way alone, which contains roughly 100 billion stars, may host at least as many planets. This staggering possibility hints at a universe teeming with worlds. Data from powerful telescopes like Kepler have revealed an incredible diversity of exoplanets, orbiting in an astonishing variety of configurations. Some lie close to their stars, tightly packed in compact systems, while others are distant gas giants far from their suns. Many exoplanets reside within the so-called habitable zone, the sweet spot where conditions might allow liquid water to exist, a crucial ingredient for life as we know it. Intriguingly, a significant number of stars are now known to host Earth-sized planets within these habitable zones, raising profound questions about the potential for life beyond our own planet. The formation of rocky, terrestrial planets requires several key conditions within a protoplanetary disk. First and foremost, there must be enough solid material, such as metals and silicates, which condense into solid particles closer to the star where temperatures are higher. This contrasts sharply with the outer, colder regions of the disk, where gases dominate and icy bodies form. The growth of these solid particles through accretion, where dust and ice collide and stick, is fundamental. As these particles coalesce into larger bodies, gravity grows stronger, pulling in more material and accelerating planet formation. The abundance and distribution of solid material alongside the collision rates dictate how efficiently and quickly planets can grow. As observational technology advances, particularly with the advent of the James Webb Space Telescope, our ability to explore these distant worlds and their atmospheres will sharpen. We stand on the brink of uncovering new insights into the abundance of planets, their compositions, and the tantalizing possibility of life beyond our solar neighborhood. Each discovery not only expands our knowledge, but also connects us more deeply to the vast, mysterious cosmos we call home. The dynamics within a protoplanetary disk play a vital role in shaping the birth of rocky planets. This swirling disk of gas and dust must strike a delicate balance. It needs to remain stable enough to allow particles to gradually stick together and grow over time, yet also be dynamic enough to encourage those crucial early collisions. Turbulence within the disk stirs the environment, helping to gather solid materials into concentrated patches and sparking interactions among particles that are the seeds of planetary formation. The surrounding conditions also matter greatly. Factors such as the young star's distance from the forming planet and the presence of volatile substances like water vapor influence what kind of world emerges. For instance, a rocky planet ideally forms within the star's habitable zone, a region where temperatures permit liquid water to exist. While this zone isn't strictly necessary for the initial building of the planet, it plays a major role in shaping the planet's future potential for life. All these elements combine to create the complex, evolving environment of the protoplanetary disk, where countless variables interact and influence one another. This intricate dance of physics and chemistry sets the stage for the incredible diversity of rocky planets we see across the cosmos. Gas giants and ice giants, meanwhile, come into being through similar yet distinct processes, shaped by the materials and conditions found in the colder outer reaches of the protoplanetary disk. In these chilly zones, volatile compounds such as hydrogen, helium, water, ammonia, and methane can condense into solid and liquid forms, providing the raw ingredients for these massive worlds. The birth of gas giants like Jupiter and Saturn begins with the same initial step as rocky planets. Small particles clump together into larger bodies called planetesimals. Once a solid core grows large enough, likely several times the mass of Earth, gravity takes over in a dramatic way. This massive core can pull in and hold onto vast amounts of gas from the surrounding disk, allowing the planet to rapidly build a thick atmosphere made mostly of hydrogen and helium. This phase is critical because the gas in the disk will eventually dissipate, driven away by the radiation and stellar winds from the young star. Ice giants such as Uranus and Neptune share a similar early history, but their final form differs significantly. Their cores grow in the same way, but they gather far less gas relative to their solid mass. Instead, their outer layers contain a higher proportion of icy and rocky materials, which gives them a unique composition compared to their gas giant cousins. These differences can be traced back to the specific conditions in the parts of the disk where they formed, regions that favored the accumulation of ices and volatiles. Both gas giants and ice giants wield tremendous gravitational influence during their early development. Their strong gravity can reshape the orbits of smaller objects nearby, sending some hurtling toward the inner solar system or capturing others as moons. The timing of their formation, the materials they gather, and their position within the protoplanetary disk all weave together to create the rich variety of planetary systems observed throughout the universe today. Comets and asteroids are vital players in the grand drama of planetary system formation. These small celestial wanderers are much more than mere space rocks. They are the ancient relics of our cosmic past, holding the secrets of how planets came to be. Born from the primordial clouds of dust and gas that surrounded young stars, these bodies carry within them the raw materials and clues essential to understanding the birth and evolution of planetary systems. Asteroids mostly take shape in the warmer inner regions of the swirling protoplanetary disk, where rocky and metallic materials clump together under gravity's gentle pull. These regions are close enough to the young star to be hot, allowing solid rock and metal to dominate. In stark contrast, comets form in the outer, colder reaches of the disk, where temperatures plunge so low that ice and gas prevail. Here, frozen water, carbon dioxide, and other ices mix with dust and rocky debris to create icy travelers that hold a rich cocktail of primordial substances. During the early stages of planet formation, asteroids and comets act as both the building blocks and delivery agents of crucial planetary ingredients. As tiny grains collide and stick to form planetesimals, bodies ranging in size from meters to kilometers, these objects grow by accreting more material, gradually forming protoplanets. When these larger bodies collide with asteroids, they incorporate new minerals and metals, enriching their chemical makeup. Such impacts can also spark the birth of moons or ignite geological transformations by generating heat and influencing the atmosphere's evolution. Comets, meanwhile, are cosmic couriers delivering precious cargo to the inner planets. Their icy cores harbor water and organic molecules, some of the very compounds thought to be essential for life. It is widely believed that during the solar system's late heavy bombardment phase, comets impacted Earth and other rocky planets, potentially seeding them with liquid water and organic building blocks. These icy visitors thus may have played a pivotal role in setting the stage for life's emergence. What makes comets and asteroids even more fascinating is their preservation of early solar system conditions. Unlike planets that have undergone extensive geological and atmospheric changes, these small bodies have remained relatively unchanged for billions of years. Scientists study their composition to peer back in time, unlocking clues about the environment and processes at work during the infancy of our solar system. Earth itself was born roughly 4.5 billion years ago from the swirling solar nebula, a vast, rotating disk of gas and dust encircling the newborn sun. This nebula was enriched by the remnants of earlier stars, making it rich in heavier elements necessary for planet formation. As the nebula cooled, dust and ice particles began to collide and stick together, gradually forming planetesimals that would eventually become planets. Through a process called accretion, these planetesimals attracted more material due to gravity, growing into larger bodies known as protoplanets. Earth emerged from one such protoplanet, growing through countless collisions that released intense heat. This heat kept the young planet molten, allowing it to differentiate into layers. The dense metals sank to form the core, while lighter silicates rose to create the mantle and crust. One of the most dramatic events in Earth's early history was a colossal collision with a Mars-sized body named Theia. This impact sent massive amounts of debris into orbit around Earth, which eventually coalesced to form the Moon. The aftermath of this giant collision, combined with continuous bombardment by leftover planetesimals, profoundly shaped Earth's surface, atmosphere, and overall evolution. Over time, as the planet cooled, stable oceans formed, and the atmosphere developed, creating a dynamic environment ripe for the origin of life. Inside Earth, the core solidified into a layered structure. A solid inner core surrounded by a liquid outer core, composed mainly of iron and nickel. The churning motion of this liquid outer core generates Earth's magnetic field, a protective shield that helps sustain life on the surface. In essence, comets and asteroids are not just cosmic debris. They are the storytellers of our solar system's formation and the crucial ingredients that made Earth and possibly other planets habitable. Their study continues to illuminate the pathways through which planets arise and evolve, revealing the profound interconnectedness of all celestial bodies in our cosmic neighborhood. Conversely, lighter materials such as silicates and other less dense minerals rose to the surface, gradually shaping the outer layers of our planet. These lighter elements formed the mantle and crust, creating a layered structure that defines Earth's geology. The mantle, positioned above the dense core, is made up of semi-solid rock that flows slowly over millions of years. This slow movement plays a vital role in tectonic processes, including the shifting of Earth's plates. Together, the upper mantle and the rigid surface layer create the crust, the thin outer shell of Earth where continents and ocean floors exist. The process of differentiation, which separated Earth's materials by density, was fundamental not only in creating these layers, but also in influencing the planet's geological and atmospheric history. As the dense core formed, it generated tremendous heat and gave rise to Earth's early magnetic field. Meanwhile, the crust and mantle continued evolving through volcanic activity, plate tectonics, and erosion, setting the stage for Earth's dynamic surface. This intricate layering and continuous activity formed the foundation of a complex geological system that ultimately made the planet hospitable for life. One of the most fascinating questions about Earth's history is the origin of its water. Scientists believe it came from a combination of internal and external sources. A primary theory suggests that water originated from volcanic outgassing, when water vapor and other gases escaped from Earth's interior as it cooled after formation. This water vapor condensed to form the earliest bodies of water, including oceans. However, a significant amount of Earth's water likely arrived from space, carried by water-rich comets and icy bodies during a turbulent era known as the Late Heavy Bombardment, about 4 billion years ago. During this chaotic period, countless asteroids, comets, and planetesimals bombarded Earth, delivering volatile compounds such as water ice. These impacts helped create the vast oceans we know today, In addition to comets, some scientists point to a class of water-rich asteroids called carbonaceous chondrites as important contributors. These asteroids are not only rich in water, but also contain organic molecules, suggesting that Earth's essential building blocks for life may have arrived through these celestial visitors. Over time, these combined processes enabled Earth to gather vast amounts of water, creating the conditions necessary for life to develop. The interaction of water, rock, and atmosphere has continued to shape the planet, making water a defining feature of Earth's identity and ecology. The late heavy bombardment itself marks a dramatic chapter in our solar system's history. Roughly 4 billion years ago, the inner solar system experienced a spike in asteroid and comet impacts lasting hundreds of millions of years. This bombardment is well studied through lunar craters, which remain well preserved because the moon lacks an atmosphere and active geology. On Earth, the consequences of this bombardment were profound. The impacts reshaped the landscape, forming craters, igniting volcanic activity, and melting surface materials. The heat from these collisions likely triggered massive volcanic eruptions, releasing gases that influenced Earth's early atmosphere and climate. Most crucially, the late heavy bombardment is thought to have delivered water and organic materials essential for life. Many impacting bodies were rich in water and organic compounds, seeding Earth with the raw ingredients needed for life's emergence. While the bombardment made Earth's surface temporarily inhospitable, the planet's subsequent cooling and ocean formation created an environment where life could begin. In this way, the late heavy bombardment stands as a pivotal era, reshaping Earth's early environment and setting the stage for the rise of life in the billions of years that followed. Shortly after Earth formed about 4.5 billion years ago, its atmosphere began to take shape. Initially, the young planet was a molten mass, but as it cooled, gases such as water vapor, carbon dioxide, ammonia, and methane were released from the interior through volcanic activity. This outgassing process created the first atmosphere, enveloping the planet and setting the foundation for future atmospheric development. However, the early conditions on Earth were far from welcoming. During this primordial era, the planet was engulfed in extreme heat, with temperatures soaring to unimaginable levels, and the atmosphere was virtually devoid of oxygen. As Earth gradually cooled over millions of years, a remarkable transformation began. Water vapor in the thick, steaming atmosphere started to condense, giving rise to the first vast oceans. These ancient bodies of water were not merely passive features of the landscape. They played a pivotal role in shaping the evolution of Earth's atmosphere. The oceans acted as giant reservoirs, absorbing vast amounts of carbon dioxide from the atmosphere. This process significantly reduced the greenhouse effect, leading to further cooling of the planet's surface. At the same time, microscopic life forms began to emerge in these watery environments. Among them were cyanobacteria, remarkable photosynthetic organisms that would change the course of Earth's history. These tiny organisms harnessed sunlight to produce energy, releasing oxygen as a byproduct. This gradual release of oxygen set the stage for one of the most dramatic shifts in Earth's atmospheric evolution, the Great Oxygenation Event. Approximately 2.5 billion years ago, this event marked a profound turning point. Oxygen levels in the atmosphere increased dramatically, fundamentally altering its composition. This influx of oxygen allowed for the rise of aerobic or oxygen-dependent life forms, which thrived in ways previously impossible. The surge in oxygen also led to the formation of the ozone layer, a protective shield high in the atmosphere that blocks harmful ultraviolet radiation from reaching the surface, enabling life to flourish more safely on land. Earth's atmosphere has continued to evolve ever since, shaped by complex interactions among geological forces, biological activity, and, in recent times, human influence. Today, our atmosphere is primarily made up of nitrogen and oxygen, with trace amounts of other gases playing crucial roles. However, human activities, especially the burning of fossil fuels, have begun to alter the atmospheric balance, raising urgent concerns about climate change and environmental degradation. Understanding how Earth's atmosphere formed and evolved is not just an academic pursuit. It is vital for predicting the future health of our planet. The story of Earth's dynamic past extends beyond its atmosphere to the very structure of the planet itself. Evidence for the early movement of tectonic plates comes from multiple lines of investigation. Geological formations, fossil records, and the distribution of ancient rock types all point to a world shaped by drifting continents and shifting plates. One of the most compelling pieces of evidence is the striking fit of continental coastlines. The shores of Africa and South America, for example, align like pieces of a puzzle, suggesting they were once united as part of a vast supercontinent before drifting apart, a concept known as continental drift, which eventually led to the modern theory of plate tectonics. Mountain ranges also tell this geological story. The Appalachian Mountains in North America share remarkable similarities with the Caledonian Mountains in Scotland, indicating these distant regions were once connected. Volcanic rocks found in ancient mountain belts, along with patterns of seafloor spreading observed at mid-ocean ridges, further confirm that tectonic processes have been ongoing for billions of years. New crust is continuously formed as tectonic plates pull apart, demonstrating the Earth's ever-changing surface. Fossils add another piece to this puzzle. Identical species found on continents now separated by vast oceans indicate these land masses were once linked. The reptile Mesosaurus, for instance, has been discovered in fossil records in both South America and Africa, reinforcing the idea of past continental cohesion. Additionally, ancient rocks dating back between 3 and 2 billion years reveal evidence of subduction zones, where one tectonic plate is forced beneath another. This shows that even early in Earth's history, dynamic tectonic activity was reshaping the planet's crust. All of this geological and biological evidence converges to paint a vivid picture of a restless planet, where the forces of plate tectonics have shaped the Earth's surface through deep time, influencing the distribution of life and land itself. Turning to the origins of life, current scientific theories propose several distinct pathways for how life might have begun. These hypotheses explore a variety of environments and mechanisms that could have given rise to the first living organisms. From deep-sea hydrothermal vents to shallow, sunlit pools, each theory seeks to unravel one of the greatest mysteries of our planet, the emergence of life from non-living matter. This ongoing inquiry not only deepens our understanding of Earth's past, but also informs the search for life beyond our planet. One of the most influential and widely discussed ideas about the origin of life is the primordial soup hypothesis. This concept imagines the early Earth as a vast, watery environment teeming with a rich mixture of organic compounds. These molecules, thought to be the building blocks of life, may have formed from much simpler chemicals such as methane and ammonia. Energy sources that were abundant in the planet's youth, such as powerful lightning storms or the relentless ultraviolet rays from the sun, could have driven the transformation of these simple molecules into more complex organic substances. This idea gained significant traction through landmark experiments, most famously the Miller-Urey experiment, which recreated early Earth conditions in a laboratory setting and successfully produced amino acids. Amino acids are fundamental because they are the building blocks of proteins, essential components of all living organisms. Alongside the primordial soup theory stands another well-supported explanation, the hydrothermal vent hypothesis. This theory proposes that life might have begun not in shallow pools or oceans, but rather around deep-sea hydrothermal vents. These vents are cracks in the ocean floor where superheated, mineral-rich water gushes out from beneath the Earth's crust. The extreme heat, combined with a cocktail of chemicals released in these environments, creates a unique and dynamic setting that could foster the formation of complex organic molecules. Proponents of this idea argue that these vent ecosystems may have offered the perfect conditions for the earliest biological processes, essentially acting as natural laboratories for life's first sparks. This view also highlights the extraordinary adaptability of life, showing that it can thrive in harsh, extreme environments previously thought inhospitable. A third major theory broadens the perspective even further by suggesting that life on Earth may have extraterrestrial origins. Known as the panspermia hypothesis, this idea raises the possibility that microbial life, or at least the essential building blocks for life, were delivered to our planet through comets, meteoroids, or interstellar dust particles. The discovery of hardy organisms such as tardigrades, tiny creatures capable of surviving extreme radiation, vacuum, and temperature fluctuations, lends plausibility to this scenario. If life or its precursors can survive such harsh conditions, it opens the door to the fascinating possibility that Earth's biological beginnings might be connected to the wider cosmos. Finally, there is the RNA world hypothesis, a theory focused on a crucial molecule called ribonucleic acid, or RNA. According to this view, RNA was the precursor to life as we know it, playing a dual role as both the carrier of genetic information similar to DNA and as a catalyst that drives biochemical reactions, much like modern proteins do. This self-replicating, self-sufficient RNA system would represent a critical evolutionary step, bridging the gap from simple chemical compounds to the complex cellular life forms that eventually emerged. The RNA world hypothesis has garnered strong scientific support because it addresses a key puzzle: how life might have managed to store information and catalyze essential reactions before the advent of DNA and proteins. While these theories may seem distinct, they are not necessarily in conflict. It is entirely possible that multiple mechanisms contributed to the emergence of life, and ongoing research continues to unravel this profound mystery. The journey from lifeless chemistry to the rich diversity of life on Earth is a story still being written. To truly understand these theories, we must consider the environment of early Earth itself, a world vastly different from the one we inhabit today. Around 4.5 billion years ago, the planet was a hot, volatile place dominated by intense volcanic activity. The surface was a turbulent landscape with oceans of molten magma covering much of the globe. As the Earth gradually cooled, it endured relentless bombardment from asteroids and comets, shaping its surface through repeated, violent impacts. These collisions not only sculpted the land, but also released gases trapped deep within the Earth. As temperatures continued to drop, water vapor from volcanic eruptions began to condense, giving rise to Earth's first oceans. These ancient seas were likely acidic and rich in dissolved minerals, setting the stage for complex chemical reactions. The atmosphere at that time was nothing like today's breathable air. Instead, it was dominated by carbon dioxide, nitrogen, water vapor, and other gases like methane and ammonia. Importantly, there was little to no free oxygen available, meaning any early life would have been anaerobic, thriving in oxygen-free environments. Surface temperatures fluctuated dramatically, influenced by greenhouse gases such as carbon dioxide that trapped heat and created a warm, humid climate in some regions. Other areas, however, faced extreme temperature swings. The presence of hydrothermal vents on the ocean floor added further complexity. These vents spewed heated, mineral-laden water that formed distinct, chemically rich habitats. These unique conditions could have provided the chemical energy needed to power the earliest life forms. Over millions of years, the interplay between geological upheaval and atmospheric evolution gradually stabilized Earth's environment. This stability was crucial, paving the way for the emergence and evolution of life. By studying these early conditions, scientists gain invaluable insight into how life could have originated and adapted, ultimately leading to the complex ecosystems we see flourishing today. The story of life's beginning is a remarkable testament to the power of chemistry, geology, and the resilience of life itself. The RNA world hypothesis stands as one of the most fascinating and influential scientific theories about the origin of life on Earth. It proposes that before the complex molecules we are familiar with today, such as DNA and proteins, there existed a simpler molecule, ribonucleic acid, or RNA, that played a central role in the earliest forms of life. According to this idea, life did not start with DNA or proteins, but rather with RNA molecules capable of both storing genetic information and catalyzing essential biochemical reactions. Imagine the primordial Earth billions of years ago, a world filled with simple organic compounds. In this chaotic environment, RNA molecules emerged as the first self-replicating entities, acting as both the blueprint and the machinery needed to sustain and propagate life. This dual functionality sets RNA apart from DNA, which mainly serves as a stable storage medium for genetic instructions. RNA's ability to fold into various three-dimensional shapes gives it a catalytic edge, enabling it to speed up chemical reactions, much like proteins do. This makes RNA not just a passive carrier of information, but an active player in the chemical processes that underpin life. Laboratory experiments have brought this hypothesis from theory closer to reality. Scientists have successfully synthesized RNA molecules that can replicate themselves and perform catalytic functions in controlled settings. These breakthroughs suggest that under the right environmental conditions, RNA-based life could have emerged naturally from simpler molecules present in the prebiotic world. Such experiments support the idea that RNA was the critical stepping stone from non-living chemistry to living biology, bridging the gap to more complex life forms. The RNA world hypothesis also has profound implications for how we understand biological evolution. If RNA was the precursor to DNA and proteins, studying these early molecules could reveal vital clues about the mechanisms through which life adapts, evolves, and diversifies over time. This perspective encourages scientists to rethink the origins of life, not as a sudden event, but as a gradual, stepwise process influenced by chemical and environmental factors on early Earth. How exactly did these first self-replicating molecules come into being? The answer likely lies in the unique conditions of the primordial Earth. Researchers theorize that simple organic molecules such as amino acids and nucleotides, the building blocks of RNA, formed in environments like hydrothermal vents or shallow, warm ponds. These settings provided the right conditions for molecules to come together and polymerize into longer chains. For example, as water evaporated from pools, it could concentrate nucleotides, allowing them to link up into primitive RNA strands without the need for enzymes. Minerals may have played a critical role by acting as catalysts, promoting the formation of longer and more complex nucleic acid chains. Once formed, these early RNA-like molecules could replicate by using themselves as templates to produce complementary strands. This replication was not perfect. Small errors introduced variations among molecules, driving an early form of natural selection. Variants that replicated more efficiently would become more common, setting the stage for evolutionary dynamics billions of years before the first cells. Environmental diversity likely contributed to this process, with different prebiotic molecules and conditions shaping the path of molecular evolution. The interplay between chemical properties and surroundings created a fertile ground for the emergence of early, self-replicating systems. Although many details of this transition remain elusive and under active investigation, the RNA world hypothesis provides a compelling narrative of life's gradual emergence, from simple organic molecules to the complex biochemical networks that define life today. Ultimately, this theory reshapes our understanding of life's beginnings, highlighting RNA as the molecule that not only carried genetic information, but also drove the chemistry of life's earliest steps. As research continues, unraveling the mysteries of the RNA world could unlock deeper insights into the fundamental nature of life and its remarkable journey on our planet. Hydrothermal vents have long fascinated scientists as potential cradles for the origin of life on Earth. These extraordinary underwater formations, found along the vast mid-ocean ridges, offer a remarkable and unique environment where the very first spark of life may have ignited. Deep beneath the ocean's surface, where sunlight never penetrates, hydrothermal vents spew superheated, mineral-rich water from cracks in the Earth's crust. This water, heated by intense geological forces, rises through chimneys and fissures, creating an environment defined by extreme heat, crushing pressure, and a cocktail of diverse chemicals. Such harsh conditions might sound inhospitable at first, but they create a dynamic, chemically rich setting that is unlike anywhere else on the planet. This environment could have provided the perfect laboratory for the chemical reactions necessary to form life's earliest building blocks. One of the most important features of hydrothermal vents is their ability to generate energy through geological processes. As minerals are oxidized by reactions fueled by the Earth's internal heat, they release chemical energy that early life forms could have harnessed. This challenges the traditional idea that sunlight was the only energy source for life's beginnings, suggesting instead that life may have first emerged in these dark, nutrient-dense underwater realms where chemical energy was abundant. Within these mineral-laden waters, simple organic molecules could have gradually formed. Over time, these molecules may have combined and transformed into more complex compounds, setting the stage for life's molecular machinery. The structure of the vents themselves, particularly their towering chimneys, likely played a vital role by trapping and concentrating these chemicals. These chimney-like formations create tiny microenvironments with stable conditions that favor chemical reactions, allowing molecules to link together into longer chains, a crucial step toward creating the polymers necessary for life, such as amino acids and nucleotides. Surrounding these vents, thriving communities of extremophiles, organisms that survive in extreme heat and pressure, offer a glimpse into what life near the dawn of time might have looked like. Some scientists propose that life did not just begin near these vents, but may have directly evolved from these resilient microbial communities. These organisms feed on the chemical energy released by the vent fluids, illustrating how early life could have thrived without sunlight, using the Earth's internal chemistry as its fuel. This suggests that hydrothermal vents were not only birthplaces for life's building blocks, but also safe harbors where primitive life forms could survive, adapt, and evolve. Research into the origins of life continues to be an interdisciplinary adventure, blending chemistry, biology, geology, and planetary science. Scientists strive to recreate the conditions of early Earth in laboratories, aiming to uncover how life's complex chemistry could have started. By simulating volcanic activity, high temperatures, and the mixture of gases that filled Earth's primitive atmosphere, researchers attempt to mimic the primordial soup from which life emerged. One landmark experiment in this field is inspired by the Miller-Urey experiment, where a mix of gases thought to represent the early atmosphere was exposed to electric sparks to simulate lightning. This experiment successfully produced amino acids, the essential building blocks of proteins, demonstrating that simple organic molecules could arise under conditions thought to mirror the early Earth. These experiments help scientists understand how the first steps toward life's complex chemistry might have unfolded. Beyond amino acids, researchers also focus on the mysterious molecule RNA, which may have been crucial in life's beginnings. RNA is unique because it can both store genetic information and catalyze chemical reactions, making it a prime candidate for the earliest self-replicating molecules. Laboratory studies investigate how RNA molecules could have formed spontaneously from simpler nucleotides under early Earth conditions, and whether RNA strands could replicate without enzymes. This research sheds light on the RNA world hypothesis, which suggests that life passed through a stage where RNA was the primary genetic material before DNA and proteins took over. The role of minerals, especially those found near hydrothermal vents, is also a major focus. These mineral surfaces may have acted as catalysts, encouraging organic molecules to join together and form more complex structures. By exposing organic compounds to minerals under simulated vent conditions, scientists are piecing together how life's fundamental components might have assembled and evolved into self-replicating entities. Through these meticulous laboratory experiments and deep-sea explorations, researchers continue to unravel the intricate story of life's beginnings. Hydrothermal vents stand as a compelling natural laboratory, illustrating how Earth's unique geology and chemistry combine to transform simple molecules into the complex tapestry of life we see today. This ongoing research not only brings us closer to understanding our own origins, but also informs the search for life on other worlds, where similar conditions might exist deep beneath alien oceans. One of the deepest and most captivating mysteries in science revolves around the origins of life on our planet. The earliest life forms on Earth were incredibly simple, single-celled organisms called prokaryotes. These tiny pioneers emerged roughly 3.5 to 4 billion years ago, at a time when Earth was still young, volatile, and hostile. The dominant prokaryotes, bacteria and archaea, were defined by their simple cellular design. They lacked a nucleus and membrane-bound organelles, which made their structure far less complex than the cells of plants and animals we see today. This simplicity, however, was a powerful advantage. It allowed these microorganisms to survive and thrive in an astonishing variety of environments, including some of the most extreme and unforgiving places on Earth. Many of these early life forms were anaerobic, meaning they did not require oxygen to survive. a necessity at a time when Earth's atmosphere contained almost no free oxygen. Instead, they relied on other, more primitive metabolic pathways to extract energy from their surroundings. Some harnessed the power of chemosynthesis, a process that uses inorganic molecules like hydrogen sulfide or methane to create energy, enabling them to flourish in dark, hostile environments such as hydrothermal vents and the deep ocean floors where sunlight never reached. Evidence for these ancient life forms comes from fossilized structures called stromatolites. These layered rock formations were created by the activity of microbial mats, mostly made up of cyanobacteria, some of the earliest photosynthetic organisms. Cyanobacteria played a monumental role in Earth's history by producing oxygen as a byproduct of photosynthesis. As these microscopic organisms spread across the oceans, they gradually transformed the planet's atmosphere during what is now called the Great Oxygenation Event, approximately 2.5 billion years ago. This event caused a dramatic rise in atmospheric oxygen, setting the stage for the evolution of more complex life. Genetic studies of modern organisms reveal that all life shares certain common genetic traits, pointing back to a universal ancestor. This genetic link connects the simplest of early life forms to the immense diversity of plants, animals, and microbes that inhabit the Earth today. Understanding these primordial life forms is crucial. It sheds light on the evolutionary processes that shape the biological world and the incredible adaptability of life. Around 2.7 billion years ago, photosynthesis became a game changer in Earth's biological history. Early photosynthetic organisms, especially cyanobacteria, developed the remarkable ability to convert sunlight into chemical energy, using carbon dioxide and water as raw materials. This process released oxygen as a waste product, which slowly but steadily transformed the Earth's atmosphere. Before this transformation, the atmosphere was dominated by gases like carbon dioxide, methane, and ammonia, with very little free oxygen present. The rise of photosynthesis and the consequent oxygen production was a turning point of immense importance. The increasing oxygen levels eventually led to the Great Oxygenation Event. This rise in oxygen had profound effects on life. Many anaerobic organisms unable to cope with oxygen's toxic effects vanished, while others adapted or evolved. Oxygen enabled the development of aerobic respiration, a far more efficient way to produce energy, which opened new possibilities for life. It allowed organisms to grow larger, become more complex, and exploit new environments. Moreover, the buildup of oxygen contributed to the formation of the ozone layer, a protective shield that blocks harmful ultraviolet radiation from the sun. This protection made Earth's surface more hospitable, paving the way for life to move from oceans onto land. The impact of photosynthesis on Earth's atmosphere and biosphere is nothing short of revolutionary. It fundamentally changed the chemistry of the planet, creating the conditions necessary for the vast diversity of life we see today. The oxygen produced by early photosynthetic life laid the foundation for all aerobic organisms and triggered a cascade of geological and climatic changes that continue to shape our world. This profound transformation marks one of the most significant chapters in the story of life on Earth. Through the ancient and remarkable process of photosynthesis, life on Earth did more than just adapt to its environment. It fundamentally transformed the very air we breathe and laid the groundwork for all future evolutionary breakthroughs. This transformation reached a crucial turning point around 2.5 billion years ago in an event known as the Great Oxygenation Event, sometimes called the Oxygen Crisis. This moment in Earth's deep history was defined by a sudden and dramatic rise in atmospheric oxygen, an element that was virtually absent before then. Long before this event, Earth's atmosphere was a starkly different place, almost completely devoid of free oxygen. Instead, it was dominated by anaerobic conditions, where life flourished without the need for oxygen. The principal architects of this change were tiny, ancient microbes called cyanobacteria. These microorganisms began producing oxygen as a byproduct of photosynthesis, releasing it into the atmosphere. As oxygen levels climbed, the world was forever altered. The surge of oxygen wrought profound consequences for life and the planet itself. Many anaerobic organisms, which had thrived in oxygen-poor environments, suddenly found themselves in a hostile world. Unable to survive the oxidative onslaught, these life forms faced widespread extinction. Meanwhile, the oxygen reacted chemically with elements in the environment, especially iron dissolved in Earth's early oceans. This reaction precipitated iron oxides, creating distinctive geological features known today as banded iron formations, which still provide clues to this transformative chapter in Earth's history. As oxygen continued to build up, it paved the way for the creation of the ozone layer, a protective shield high in the atmosphere that absorbs harmful ultraviolet radiation from the sun. This new barrier was a game changer. It allowed life to escape the watery depths and begin colonizing land, opening up entirely new evolutionary possibilities. The Great Oxygenation Event was much more than a shift in atmospheric chemistry. It was the catalyst that led to the rise of aerobic organisms, capable of harnessing oxygen to fuel more complex and energy-demanding forms of life. This moment set Earth on a new evolutionary trajectory, leading to the emergence of multicellular organisms and the rich biodiversity we witness today. Around 600 million years ago, during the Ediacaran period, the foundations for multicellular life began taking shape. Before then, life was largely composed of single-celled organisms. The first step towards complexity came in the form of simple colonial organisms, groups of cells living together in loose communities. These colonies offered significant advantages. Cells could cooperate, share resources, and even specialize. Some might focus on gathering nutrients, while others handled reproduction, boosting their collective survival. As these colonial organisms evolved, they developed more sophisticated ways to communicate and cooperate. This growing interdependence was crucial because it enabled cells to function better as a unit than they ever could alone. Over time, genetic regulation played a key role, allowing certain cells within these groups to take on specific roles by controlling gene expression. This cellular differentiation transformed colonies into truly multicellular organisms, with division of labor becoming a hallmark of their biology. Environmental shifts, including rising oxygen levels, further fueled this evolutionary leap. New ecological opportunities emerged, encouraging a vast experimentation with body plans and cellular arrangements. This led to the incredible diversity of multicellular life, from simple algae and sponges to complex plants and animals. The interplay of cooperation, specialization, and genetic innovation has propelled life to adapt and flourish in countless forms throughout Earth's long history. In sum, the emergence of complex life was driven by groundbreaking evolutionary innovations. Photosynthesis first altered the planet's atmosphere, creating conditions for oxygen-dependent life. Later, the rise of multicellularity transformed single cells into integrated, cooperative organisms capable of remarkable complexity. These milestones not only shaped the trajectory of life, but also set the stage for the vast, interconnected ecosystems that define our world today. One of the earliest and most groundbreaking evolutionary leaps was the emergence of multicellularity itself. This remarkable innovation allowed individual cells to join forces, forming cooperative groups where cells could specialize in distinct roles. Such specialization meant that organisms could develop different cell types, each with unique functions, paving the way for far more complex structures and systems. This complexity enabled these organisms to perform a variety of tasks much more efficiently than their single-celled predecessors ever could. Following closely behind, another transformative breakthrough was the evolution of sexual reproduction. Unlike asexual reproduction, where a single organism creates an identical copy of itself, sexual reproduction involves the blending of genetic material from two separate parents. This mixing of genes significantly increased genetic diversity within populations, which in turn enhanced their adaptability and resilience. By introducing a rich variety of genetic combinations, sexual reproduction played a vital role in the rise of complex traits and empowered organisms to better respond to ever-changing environments. At the same time, the development of internal and external skeletons marked a major turning point in the evolution of complexity. The appearance of hard body structures allowed organisms not only to grow larger, but also to protect themselves from predators. Invertebrates like arthropods and mollusks developed exoskeletons, external shells that offered defense and support, while vertebrates evolved internal skeletons to provide a framework for movement and growth. These skeletal innovations supported increased body size, facilitated more sophisticated movement, and opened the door to new ecological niches, letting organisms explore habitats previously inaccessible. Equally important was the evolution of specialized tissues and organs within multicellular life. As organisms grew more complex, dedicated systems for digestion, circulation, and respiration emerged, allowing them to support larger bodies and more active lifestyles. For instance, the development of efficient circulatory and respiratory systems in animals enabled the effective transport of nutrients and gases, which powered higher metabolic rates and greater mobility. This advancement allowed animals to become more dynamic and responsive to their surroundings. Moreover, the rise of new ecological interactions, such as predation and symbiosis, greatly accelerated evolutionary diversification. These relationships created selective pressures that spurred the development of advanced traits, including sharper sensory organs, better defense mechanisms, and complex behavioral strategies. Each innovation built upon the last, weaving a complex web of life that eventually blossomed into the extraordinary diversity we witness on Earth today. Together, these evolutionary milestones laid the foundation for the incredible variety of complex organisms that inhabit our planet. However, the story of life's evolution has not been a smooth journey. Mass extinction events have played a profound role in shaping the course of evolution by drastically transforming ecosystems and creating fresh opportunities for new forms of life to rise. Throughout Earth's history, there have been 5 major mass extinctions, each wiping out a substantial percentage of species across many groups. While these events caused significant loss, they also fundamentally reshaped ecological dynamics and opened up niches for the survivors to exploit. One of the most well-known mass extinctions occurred at the end of the Cretaceous period, about 66 million years ago. This catastrophic event, likely caused by a combination of an asteroid impact and intense volcanic activity, wiped out the dinosaurs, the dominant terrestrial reptiles of their time. With these giants gone, mammals, previously small and inconspicuous, had the chance to diversify rapidly and fill the vacant ecological roles. This adaptive radiation laid the groundwork for mammals to evolve into a wide range of forms, including primates, marine mammals, and eventually humans. Mass extinctions have a powerful influence on evolutionary paths. After each event, the surviving species often experience rapid diversification, a process known as adaptive radiation. Freed from previous competition and facing new environmental conditions, these survivors develop novel adaptations and give rise to entirely new groups of organisms. For example, after the Permian-Triassic extinction, the deadliest mass extinction in Earth's history, many arthropods and early reptiles diversified extensively, shaping the ecosystems of the following Mesozoic era. Furthermore, mass extinctions impose strong selective pressures on remaining species, driving significant evolutionary shifts. The traits that help species survive in drastically altered environments become favored, leading to innovations in body structure, reproductive strategies, and ecological interactions. These changes not only increase biodiversity, but also propel the evolution of entirely new forms of life. In this way, mass extinction events have not merely reduced life's diversity, they have acted as powerful catalysts for evolutionary innovation. Each extinction reshaped the biosphere, setting the stage for the emergence of new adaptations and life pathways. The dynamic response of life to these dramatic changes underscores the resilience and inventiveness of evolution itself. Every mass extinction left an indelible mark on Earth's biological tapestry, continuously reshaping ecosystems and allowing the dazzling variety of life we see today to flourish. The story of human evolution is a captivating journey that unfolds within the grand narrative of primate evolution, supported by a rich tapestry of fossil discoveries, genetic research, and advances in anthropology. Humans belong to the family Hominidae, which also includes our closest living relatives, the great apes, chimpanzees, bonobos, gorillas, and orangutans. This family connection sets the stage for understanding how our species fits into the wider tree of life. Tracing the human lineage takes us back millions of years to a pivotal moment when our ancestors diverged from the common ancestor we share with chimpanzees. Scientists estimate this split happened approximately 5 to 7 million years ago, marking the beginning of a unique evolutionary path. One of the earliest known members of our lineage is Sahelanthropus chidensis, which lived around 6 to 7 million years ago. Fossils from this species reveal a fascinating blend of traits seen in both apes and later human ancestors, suggesting it played a crucial role in bridging the evolutionary gap. As time passed, a variety of hominin species emerged. Among them was Australopithecus afarensis, made famous by the fossil known as Lucy, which lived between 3 and 4 million years ago. These early ancestors displayed a remarkable combination of features. They were capable of walking upright on 2 legs, a trait known as bipedalism, while still retaining adaptations for climbing trees. This dual lifestyle reflects a transitional phase where early humans balanced life both on the ground and in the branches. The next significant step in our evolutionary story is the rise of the genus Homo, which marks a clear shift toward larger brains and more sophisticated tool use. Homo habilis, appearing around 2 million years ago, is often considered one of the earliest members of this group. Fossil evidence indicates that Homo habilis used simple stone tools, an early sign of technological innovation. Following this, Homo erectus emerged roughly 1.9 million years ago, displaying a more modern body structure, as well as the ability to control fire and craft more complex tools. This species was the first to venture beyond Africa, marking one of the earliest known migrations of hominins across the globe. Modern humans, Homo sapiens, evolved approximately 300,000 years ago in Africa. Genetic and fossil records show that as Homo sapiens developed, they coexisted and sometimes interbred with other hominin species like Neanderthals and Denisovans. These interactions have left a lasting legacy, as traces of Neanderthal and Denisovan DNA can still be found in people living today. Around 60,000 years ago, Homo sapiens began migrating out of Africa, ultimately spreading across the continents and giving rise to the rich tapestry of cultures and civilizations that define humanity today. The ongoing exploration of human evolution is a multidisciplinary adventure, weaving together genetics, paleontology, archaeology, and anthropology. Each discovery adds depth to our understanding of how early humans adapted to their environments, interacted with each other, and developed the complex behaviors that set us apart. Our ancestors were not just passive witnesses to the past. They were active participants in a dynamic process shaped by genetic, environmental, and social forces. Early hominins differed from modern humans in several significant ways. Physically, they were often more robust and smaller, with pronounced brow ridges and sloping foreheads. For example, Australopithecus afarensis had long arms suited for climbing, suggesting that life in the trees was still an important part of their existence. Their brains were smaller compared to the average modern human, which affected their cognitive abilities. While early hominins likely possessed basic problem-solving skills and used simple tools, they did not have the advanced language or complex social structures that characterize modern humans. One of the defining characteristics of Homo sapiens is our capacity for sophisticated communication and abstract thinking. These abilities helped shape the development of complex societies and cultures. Early hominins created rudimentary tools using stones and sticks, but modern humans have expanded this into an incredible range of technologies, from simple hand tools to intricate machinery. The transmission of knowledge and skills across generations has been fundamental in allowing us to reshape our environments and create civilizations unlike anything seen before. Environmental challenges, particularly climate change, played a critical role in shaping human evolution. Over millions of years, Earth's climate fluctuated through cycles of cooling and warming, altering the landscapes available to our ancestors. These changes forced early hominins to adapt, moving between forests and open savannas or migrating to new regions to survive. Such pressures influenced physical traits, behaviors, and social structures, driving evolutionary innovations. During periods of glaciation and warming, early humans expanded their diets beyond foraging for fruits and leaves to include more meat, which provided higher protein and energy intake. This dietary shift likely supported the development of larger brains and more complex cognitive functions. The ability to hunt and gather diverse foods may have been a key factor in the emergence of Homo sapiens and their evolutionary success. In essence, the evolution of humans is a complex, ongoing saga, a story of adaptation, survival, and innovation. It reveals not only where we come from, but also how deeply interconnected we are with the natural world and the other species that share our planet. This fascinating journey continues to unfold with every new discovery, enriching our understanding of what it truly means to be human. Moreover, the environmental challenges brought on by climate change in early human history created an urgent need for increased social cooperation and communication. As food sources became unpredictable and scattered, early humans found themselves relying more and more on each other for survival. This necessity nurtured strong social bonds and sparked the emergence of primitive forms of language. These early communication skills did more than just improve survival chances. They laid the essential foundation for the intricate societies that would later develop. Through collaboration and shared knowledge, early humans were able to exchange ideas and technologies that propelled their collective progress forward. Understanding climate change also helps explain the migration patterns of our ancient ancestors. As their habitats shifted and transformed, groups of early humans dispersed across vast continents, searching for more hospitable living conditions. This migration led them into contact with diverse environments and climates, influencing their genetic diversity and ability to adapt. The constant interplay between shifting climates and human adaptability has been a powerful driving force throughout our evolutionary history, showing just how deeply intertwined our species has always been with the Earth's ecological changes. One of the most pivotal moments in human evolution was the development and use of tools, which dramatically affected both physical and cognitive growth. Early hominins, like Homo habilis, began crafting simple stone tools about 2 million years ago. These tools enhanced their ability to hunt, gather, and process food, opening access to a broader variety of resources. This richer, more nutrient-dense diet supported the growth of larger brains over time. As tool-making techniques improved and diversified, early humans could tackle increasingly complex tasks, which fueled advancements in technology and culture. The mastery of fire marked another revolutionary step in human development. Fire provided warmth and light, enabling early humans to extend their activities into the night and survive colder climates. More importantly, the ability to cook food transformed their diet. Cooking made food easier to chew and digest, while increasing nutrient absorption, thus providing more energy. This dietary shift likely played a crucial role in the development of larger brains and more complex social structures. Sharing cooked meals could have fostered community bonding and cooperation. The use of fire also encouraged the evolution of complex social behaviors. As early humans worked together to hunt, gather, and prepare food, they developed social networks that enhanced communication and collaboration. This reliance on teamwork eventually gave rise to more intricate societies where knowledge, skills, and resources were shared. The exchange of ideas and innovations during this time was critical not only for survival, but also for continued development and cultural growth. Advancements in tool-making and fire use reflected increasing proficiency in problem-solving and abstract thinking. These mental abilities led to innovations not just in material culture, but also in how early humans perceived and interacted with their environment. This burgeoning ingenuity laid the groundwork for the diverse technologies and rich cultural practices that define modern human life, emphasizing how essential these developments were to shaping our species. Genetic evidence has greatly deepened our understanding of human evolution, providing insights that often refine what the fossil record alone can tell us. By comparing DNA from different species, especially between ancient and modern humans, scientists have uncovered a complex web of ancestry and migration. One of the most compelling discoveries comes from studying mitochondrial DNA, which is inherited only from mothers. This genetic material has allowed researchers to trace maternal lineages back thousands of generations, giving rise to the concept of a mitochondrial Eve. This hypothetical common ancestor is believed to have lived in Africa approximately 100,000 to 150,000 years ago, underscoring the African origins of all modern humans. And additionally, the study of nuclear DNA has revolutionized our understanding of ancient human history. By sequencing the genomes extracted from fossilized human remains, scientists have unlocked a molecular time machine, one that deciphers the genetic variations that emerged across tens of thousands of years. This isn't just data, it's a biological map of how our ancestors adapted, survived, and evolved. One of the most groundbreaking revelations came from the Neanderthal Genome Project. It found that modern humans who are not of African descent carry roughly 1 to 2% Neanderthal DNA. This small but significant genetic trace is no accident. It points directly to a moment in the deep past when early Homo sapiens encountered Neanderthals and interbred with them. These ancient unions weren't merely historical footnotes. They likely shaped us in important ways. Traits such as skin color and immune system function may have been influenced by these interspecies connections, offering survival advantages in unfamiliar climates and new disease environments. But the story doesn't end with Neanderthals. Far from it. Advances in genetic technology have allowed researchers to identify another enigmatic group of archaic humans, the Denisovans. Although no complete skeleton has ever been found, DNA recovered from a single finger bone and a few teeth discovered in a Siberian cave opened an entirely new chapter in our evolutionary narrative. Today, genetic analysis shows that Denisovan DNA lives on, particularly in populations from Southeast Asia and Oceania, where some individuals carry up to 5% Denisovan genetic material. This discovery underscores an essential truth. Human evolution is not a straight line, but a tangled, interconnected web involving multiple species, interactions, and migrations. The surge in genomic technologies has further enhanced our ability to interpret this genetic legacy. Now, scientists can conduct highly detailed analyses of ancient DNA, revealing how human populations have adapted over time to drastic environmental changes. These adaptations aren't abstract. They are encoded in our very genes. For instance, the ability to digest lactose into adulthood, once rare, became common in populations that domesticated animals for milk. Similarly, skin pigmentation genes evolved in response to varying levels of ultraviolet light. In high-altitude regions such as the Himalayas or the Andes, people developed unique genetic traits that allow them to thrive despite low oxygen levels. Each of these examples is a testament to the human body's remarkable capacity to adapt, encoded into our DNA like biological bookmarks in the story of survival. All of these genetic clues help weave a vivid and intricate picture of our past, but they also intersect with another force that shaped our species profoundly: migration. From the very beginning, human history has been a story of movement. The first migrations out of Africa set off a chain reaction that would shape every corner of the globe. As early humans ventured into new territories, they encountered unfamiliar climates, landscapes, and challenges. These journeys didn't just change where we lived, they transformed who we were. The need to adapt to colder temperatures, for instance, led to lighter skin tones in northern populations to aid vitamin D synthesis under weaker sunlight. Meanwhile, communities that remained near the equator retained darker pigmentation to protect against intense ultraviolet radiation. Each adaptation is a genetic echo of a long-ago struggle with the elements. Migration also carried culture in its wake. As groups settled in new lands, they developed distinct languages, belief systems, and social structures. These differences weren't static. As migrating populations encountered one another, they exchanged ideas, tools, and customs. The spread of agriculture is a powerful example. From its origins in the Fertile Crescent, it radiated outward, revolutionizing diets and reshaping societies. People moved less, cities emerged, and trade networks began to form. Culture, like genetics, evolved, and often the two did so hand in hand. Another consequence of these global wanderings was the inevitable contact between previously isolated human groups. Interbreeding between these populations introduced new genetic material, adding even more complexity to our species' makeup. This genetic blending has tangible effects even today, influencing how different populations respond to various diseases and environmental conditions. It turns out that our susceptibility to certain illnesses, or our resilience against them, often traces back to these ancient exchanges. Ultimately, the migrations of our ancestors set into motion a continuous and dynamic process of genetic adaptation, cultural transformation, and evolutionary change. This ongoing interplay has shaped not just our biology, but our identities, communities, and shared histories. Even now, the legacy of those early movements is inscribed in our DNA, and reflected in the rich diversity of human life across the planet. We are, in every sense, the product of journeys taken long ago, shaped by the footprints of those who came before us and the genes they left behind. And so, as the threads of our genetic legacy stretch back through countless generations, they carry within them the story of survival, adaptation, and change. The remarkable diversity seen in modern populations is not just a biological fact. It is living proof of the endurance and ingenuity that have defined the human experience since its origins. Our DNA is more than a code. It is a historical map, charting the movements and choices of ancient peoples whose lives laid the foundation for the world we know today. One of the most transformative chapters in this ongoing story was the advent of agriculture, a shift so profound that it redefined not only how humans lived, but how they thought, believed, and interacted with the world around them. This transformation did not occur in a vacuum. It was the product of a long, complex interplay of natural events, social pressures, and cultural evolution. Around 10 to 12,000 years ago, the Earth was emerging from the grip of the last ice age. As glaciers retreated and global temperatures climbed, dramatic changes swept across the planet. New ecosystems bloomed where there had once been frozen tundra. Wild grains and edible plants, once rare and scattered, began to flourish in abundance. Animal populations shifted along with the vegetation, creating new patterns of availability for the hunter-gatherer bands that roamed the changing landscapes. This climatic shift did more than alter the environment. It offered an opportunity. As food sources became more predictable in certain regions, humans began to experiment with ways to control and enhance their access to them. They learned to save seeds, to clear land, to nurture specific plants over others. They began to domesticate animals, recognizing their usefulness not only as food but as labor and companionship. Slowly, the seeds of agriculture took root, first metaphorically, then quite literally. At the same time, human populations were growing. With more people came a greater need for sustenance. Nomadic life, while adaptive and resilient, imposed limits on group size and long-term stability. But in river valleys, on fertile plains, and near seasonal wetlands, people discovered they could stay in one place and still survive, even thrive. These early settlements began to form the nuclei of complex communities where food production could be scaled, stored, and shared. No longer solely focused on the immediate task of gathering food, individuals could specialize. Some became tool makers, others potters, builders, spiritual leaders, or traders. This division of labor sparked new ideas and technologies. Better plows, more efficient irrigation systems, sturdier shelters, and more intricate forms of art and record keeping. The development of pottery, for example, revolutionized how food was stored and transported, while irrigation allowed communities to extend farming into previously inhospitable terrain. A reliable food supply created surpluses. Surpluses created security, and security gave rise to culture. Cultural evolution went hand in hand with agricultural expansion. Humans are natural modifiers of their environment, but also of meaning. As they began to shape the land and its inhabitants, they forged a deeper connection to the rhythms of the earth. Crops became sacred. Livestock became symbols of wealth and power. Rituals and stories emerged to explain the harvest, the rains, and the cycles of growth and decay. Farming was no longer just survival, it was identity. Yet none of this happened in isolation. River valleys, such as those along the Nile, the Tigris and Euphrates, the Indus and the Yellow River, became the cradles of early civilization, not only because they were fertile, but because they were connected. These waterways served as lifelines for irrigation, yes, but also for exchange. They became the highways of the ancient world, allowing for the movement of goods, ideas, and people. As traders traveled between settlements, they carried more than food or pottery. They spread agricultural techniques, religious concepts, and artistic styles. The sharing of technologies and beliefs spurred cultural development and social complexity. Urban centers began to rise. Governance took shape. Writing systems emerged to record transactions, myths, and laws. The foundations of civilization, law, religion, economy, hierarchy, were laid atop the fertile soil of agriculture. Thus, the rise of farming was not a singular event, but a process, slow, multifaceted, and shaped by a convergence of forces. Environmental changes made it possible. Population pressures made it necessary. Technological advances made it sustainable. Cultural meaning made it enduring. In the end, agriculture was more than a way to feed the hungry. It was a way to reshape the human world. From the scattered camps of nomads to the bustling cities of ancient empires, from hand-dug irrigation ditches to vast networks of trade, the cultivation of land set humanity on a new trajectory, one that continues to evolve to this day. And finally, it was the abundance of natural resources coupled with growing population density that unlocked unprecedented opportunities for human specialization. As agricultural output surged, thanks to fertile soil and dependable water sources, early societies began to move beyond the boundaries of mere survival. For the first time, not everyone had to farm. Freed from the daily demands of subsistence living, individuals began to devote themselves to a wide array of emerging crafts, trades, and professions. In the heart of these ancient river valleys, artisans shaped pottery and tools, weavers spun fabric, and spiritual leaders interpreted the forces of nature and the divine. Over time, these roles solidified into more complex social hierarchies. Distinctions emerged between laborers, skilled workers, leaders, and elites, setting the foundation for structured societies. This process was not accidental, but born from necessity. As more people gathered in these settlements, the need for organization and cooperation intensified. Communities devised early systems of governance to regulate the use of shared resources, resolve disputes, and maintain communal order. These governance structures were not just about managing conflict, they were the seeds of organized political systems, systems that would grow in sophistication alongside the civilizations they served. Cultural practices flourished as people had the stability and space to develop rituals, music, art, and religious expression, adding depth and identity to these emerging urban centers. It was a convergence of vital elements: rich, arable land, constant access to fresh water, and naturally navigable trade routes. These factors enabled early river valley civilizations to grow rapidly, transforming simple agrarian villages into bustling hubs of human activity. These centers did not just survive, they flourished, becoming cradles of innovation that would profoundly shape the trajectory of human history. The emergence of cities did not happen overnight. It was the result of key innovations that revolutionized how people lived and interacted with their environment. Perhaps the most transformative was the advancement in agricultural techniques. Practices such as crop rotation and irrigation allowed for sustained farming on a scale previously unimaginable. With consistent and abundant food supplies, communities could expand their populations, leading to denser and more permanent settlements. This surplus in production had an enormous side effect. It liberated portions of the population from farming altogether. These individuals pursued specialized trades: blacksmiths, merchants, builders, and scribes, to name a few, each contributing to the complexity and vitality of urban life. The division of labor enhanced efficiency, encouraged innovation, and fostered economic growth. Equally vital was the creation of infrastructure. As communities expanded, so did their need to connect. Roads, bridges, and canals became lifelines, linking farms to markets, people to resources, and cities to one another. These transport systems didn't just support commerce, they were conduits for culture, technology, and ideas. Through trade, cities exchanged more than goods. They shared philosophies, spiritual beliefs, artistic styles, and scientific insights. Social and political organization evolved in tandem. The increasing complexity of these societies demanded more than informal agreements or tribal customs. Formal governance took shape, with leaders emerging to enforce laws, manage public works, and guide collective decision-making. Bureaucracies developed to keep records, collect taxes, and administer civic projects. This web of governance laid the groundwork for the sophisticated political institutions that would define urban life for millennia. At the same time, breakthroughs in technology reshaped the built environment. New construction materials, such as fired brick and cut stone, allowed for stronger, taller, and more permanent structures. Homes, temples, and administrative buildings became architectural achievements in themselves, reflecting the stability and pride of their inhabitants. Inventions like pottery improved food storage and cooking, while metallurgy revolutionized tools and weaponry, boosting both domestic life and military power. Together, these advances created the ecosystem in which cities could truly thrive. What began as small agricultural hamlets transformed into sprawling urban landscapes, vibrant, diverse, and resilient. Crucially, one of the most profound innovations of this era was the invention of writing systems. Initially developed out of necessity, writing emerged to record information, facilitate trade, and manage increasingly complex societies. Around 5,000 to 6,000 years ago, early civilizations like those in Mesopotamia and Egypt began using simple pictographs etched into clay or carved into stone. These symbols represented goods, quantities, and actions, serving practical functions like tracking harvests and documenting transactions. Cuneiform in Mesopotamia and hieroglyphs in Egypt were among the earliest known systems, each reflecting their culture's unique priorities and environment. Over time, writing evolved from literal depictions to abstract representations of sound and meaning. The development of syllabic and alphabetic scripts made it easier to represent spoken language, drastically expanding the range of ideas that could be captured and communicated. This democratization of writing transformed societies. It allowed knowledge to transcend time and geography. Stories, laws, myths, and scientific observations could be preserved, analyzed, and built upon by future generations. Writing became a tool not only of administration, but of culture and identity. The written word enabled the creation of legal codes that governed conduct, treaties that defined alliances, and historical records that chronicled triumphs and disasters. In doing so, it supported the rise of centralized governments and complex bureaucracies capable of managing vast territories and populations. More than just a tool of governance, writing was a spark for human thought. It gave rise to literature, philosophy, and scientific inquiry. It preserved epics and poetry, recorded astronomical charts, and captured religious doctrine. Across continents and centuries, it was the written word that allowed human civilizations to reflect on themselves, question their place in the cosmos, and imagine new possibilities. The legacy of these early innovations, from farming to cities, from governance to writing, resonates deeply within the foundations of our modern world. They were not isolated breakthroughs, but interconnected threads in the grand tapestry of civilization. Through them, early humans built the scaffolding upon which every future society would stand. Ultimately, writing systems have been fundamental in shaping the course of human civilization. They enhanced communication, preserved cultural heritage, and laid the foundation for the complex societies we live in today. But it wasn't just writing that drove progress. Trade played an equally vital role. Throughout history, trade has acted as a powerful catalyst for the spread of ideas and technologies, serving as a bridge that connected diverse cultures and sparked innovation. As civilizations began engaging in commerce, caravans, ships, and trade routes emerged as lifelines linking far-flung regions of the world. These connections allowed for more than just the exchange of goods. They created pathways for the sharing of knowledge, customs, and technological advancements. One of the most famous examples is the Silk Road, which stretched from Asia all the way to Europe. This extensive network carried valuable products like silk, spices, and precious metals, but also transported religious beliefs, artistic styles, and scientific ideas that shaped societies along the way. Consider how agricultural techniques and crops spread through these trade networks. Traders moving between different lands introduced new farming methods and plants that had evolved in distant regions. Crops such as rice traveled from Asia to Africa and Europe, while maize and potatoes made their way from the Americas to the rest of the world. These introductions helped diversify diets, improve food security, and spark changes in social structures, ultimately supporting population growth. The impact of these agricultural innovations was profound and long-lasting. Trade routes were also avenues for the diffusion of technologies that improved daily life and production capabilities. Advancements in metallurgy, textile manufacturing, and construction methods often spread as skilled artisans exchanged expertise. During the rise of empires, the demand for luxury goods fueled the adoption of cutting-edge techniques from conquered territories and neighboring cultures. For example, the transmission of papermaking technology from China to the Islamic world and eventually Europe revolutionized education, administration, and communication. Beyond tangible goods and technologies, trade encouraged the exchange of philosophical, religious, and artistic ideas, enriching the cultural fabric of societies. Traders and merchants facilitated the blending of beliefs, leading to the spread of major religions like Buddhism, Islam, and Christianity along key trade routes. Artistic styles merged and evolved, producing unique hybrid cultures in regions where commerce thrived. These complex interactions between people, goods, and ideas have profoundly influenced human history, fostering collective progress that still echoes in the modern world. Alongside trade, major energy revolutions reshaped economies and societies on an unprecedented scale. The Industrial Revolution, beginning in the late 18th century, marked a dramatic turning point with the widespread adoption of steam power. Steam engines revolutionized industries such as textiles and manufacturing, enabling mass production and significantly boosting productivity. Factories churned out goods at a scale never seen before, driving economic growth and creating new job opportunities, while also drawing large populations into emerging urban centers. Steam power also transformed transportation. The invention of steam-powered locomotives and ships drastically cut travel times and costs, reshaping trade routes and domestic markets. This newfound mobility not only sped the movement of goods, but also facilitated the exchange of ideas and cultures over vast distances. The interconnected world that emerged from improved transportation laid the foundation for globalization, opening up expanded markets and international trade networks. Following steam, the advent of electricity in the late 19th and early 20th centuries accelerated human progress even further. Harnessing electrical energy sparked innovations that profoundly changed everyday life. Cities grew brighter and more dynamic as electric lighting extended working hours and transformed urban living conditions. Electricity powered new machines and technologies, shaping modern society in countless ways. Together, these developments, writing, trade, and energy revolutions, have woven a complex tapestry of human achievement. They have driven cultural exchange, technological innovation, economic growth, and social transformation. The legacy of these forces remains visible today, reminding us of the enduring power of connection, creativity, and progress across human history. And so began a transformation that would redefine the very rhythm of daily life. The electrification of society marked one of the most pivotal turning points in modern history. The rise of electrical appliances fundamentally changed how people lived and worked, shifting the balance of daily responsibilities, especially within the home. Tasks that had once demanded hours of manual labor, laundry, cooking, cleaning, were now simplified, automated, or accelerated. This shift not only improved overall quality of life, but liberated individuals, particularly women, from the physical burdens of domestic work, allowing for expanded opportunities in education, employment, and public life. Electricity's impact, however, extended far beyond the home. It served as the catalyst for an explosion of technological innovation. With electric power came the development of the telephone and the radio, communication breakthroughs that collapsed distances and brought human voices into one another's homes, no matter how far apart. The way people interacted, shared information, and understood the world was forever altered. But the revolution did not stop there. By the mid-20th century, electricity powered another seismic shift, the invention of the computer. Once the domain of science fiction, machines capable of processing vast amounts of information at unimaginable speeds became a reality. This marked the dawn of the digital age. For the first time, humans could store, compute, and transmit data on scales never before thought possible. Commerce became instantaneous. Education moved beyond textbooks. Governments transformed how they functioned. Even personal relationships evolved in the presence of global networks that connected lives across continents in seconds. Together, these developments, the electrification of life and the digital transformation it made possible, have reshaped civilization. Industry expanded to a global scale, cities swelled into metropolises, living standards soared, and across all this, a vast and intricate web of energy-powered systems now connects the planet. Yet, this relentless progress brings with it sobering responsibilities. As humanity becomes ever more reliant on energy, societies are being called to reckon with sustainability, environmental stewardship, and the delicate balance between advancement and planetary well-being. In the background of these revolutions, a quieter but equally profound journey was unfolding: the evolving understanding of the atom. The story of the atom begins not in laboratories, but in the minds of ancient thinkers. Over 2,000 years ago, in the 5th century BCE, Greek philosophers like Democritus imagined that all matter was composed of tiny, indivisible components called atoms. These were bold, abstract ideas with no empirical support, but they planted the seeds of curiosity that would one day flourish into science. The true scientific exploration of the atom began in earnest in the 19th century with the work of English chemist John Dalton. Dalton proposed that atoms were the smallest units of matter, and that each chemical element was made of its own unique kind of atom. According to his theory, atoms combined in fixed ratios to form compounds, and they were neither created nor destroyed in chemical reactions. Dalton's work laid a systematic foundation for the study of matter and ignited a new era of chemical understanding. Then came the turn of the 20th century, and with it, revelations that would upend everything scientists thought they knew. J.J. Thomson, through experiments with cathode rays, discovered the electron, a subatomic particle far smaller than the atom itself. This discovery shattered the long-held notion of the atom as indivisible. Thomson envisioned the atom as a kind of plum pudding, with negatively charged electrons scattered throughout a positively charged matrix. But this model was soon put to the test. In 1912, Ernest Rutherford's now famous gold foil experiment revealed that the atom was mostly empty space, with a dense, positively charged nucleus at its core. Electrons orbited this nucleus like planets around a sun, giving rise to the nuclear model of the atom. Yet, even this vision would prove too simplistic. The emergence of quantum mechanics in the early 20th century transformed everything once again. Danish physicist Niels Bohr introduced a model where electrons existed in quantized energy levels, leaping from one orbit to another. While groundbreaking, Bohr's model still fell short of explaining the full behavior of electrons. It was quantum theory that ultimately rewrote the rules. Electrons, scientists learned, did not travel in fixed paths, but instead occupied probabilistic regions known as orbitals. The atom was no longer a miniature solar system, but a dynamic, complex structure governed by the strange and counterintuitive laws of quantum mechanics. Particles existed in states of probability until measured. Certainty was replaced with likelihood, and beneath it all lay a rich and intricate tapestry of interactions. This refined understanding of the atom has had ripple effects across every branch of science and technology. It has shaped modern chemistry, opened doors in nuclear physics, and revolutionized medicine through imaging and cancer treatment. It has driven the creation of semiconductors, microchips, and the electronic devices that now fill every corner of life. And still, the journey continues, as scientists probe ever deeper, exploring quarks, bosons, and the very forces that hold the universe together. The atom remains both a symbol of human curiosity and a gateway to answers we have yet to imagine. And amidst all of this, the method by which we've come to know these things, the scientific method itself, was not born fully formed. It, too, evolved over centuries, shaped by culture, philosophy, and historical upheaval. During the Renaissance and the scientific revolution, scholars began to challenge ancient dogma. They embraced observation, experimentation, and repeatability. The works of Galileo, Bacon, and Newton laid the foundations for a new way of thinking, one where questions were tested, not merely debated, and truths were pursued through evidence rather than authority. This method has guided every discovery since, from the electron to the cosmos. It is the lens through which we interpret our world, and it remains our most powerful tool in the search for understanding. And so began one of the most transformative chapters in human history, a time when the pursuit of knowledge broke free from ancient chains and surged forward with an insatiable hunger for truth. One of the key elements driving this transformation was a renewed emphasis on empirical observation and rational thought, born from a powerful resurgence of interest in the classical works of ancient Greece and Rome. Scholars like Aristotle had centuries earlier laid the intellectual foundation for systematic inquiry. But it was during the Renaissance that these ancient seeds began to flourish anew. As Europe emerged from the shadow of the Middle Ages, thinkers began to question the long-standing dogmas that had gone unchallenged for generations. The authority of the church, the rigid framework of scholasticism, and reliance on purely philosophical reasoning gave way to a bold new spirit, one rooted in skepticism, curiosity, and evidence. This shift would ignite a revolution in thought that culminated in what we now call the scientific method. In the 16th and 17th centuries, a series of visionary figures emerged, each contributing vital threads to this tapestry of discovery. Among them was Nicolaus Copernicus, whose heliocentric model proposed something truly radical for the time, that the Earth revolved around the Sun. This directly contradicted the long-accepted geocentric model, which placed Earth at the center of the universe, a view deeply ingrained in both religious doctrine and human intuition. Galileo Galilei took Copernicus's theory and gave it empirical weight. Through the use of telescopes and carefully controlled experiments, Galileo gathered observations that challenged the accepted worldview. He championed the idea that observation, what one could see, measure, and test, was essential to understanding the natural world. His work was more than a scientific achievement. It was a philosophical declaration that truth must be discovered, not inherited. Then came Johannes Kepler, who refined our understanding of planetary motion by introducing the concept of elliptical orbits. His work demonstrated that mathematical precision could explain celestial phenomena far better than age-old assumptions. Together, these figures shifted the paradigm from one of passive acceptance to active investigation. At the heart of this emerging worldview was the formulation of the scientific method, a structured approach to inquiry that prioritized observation, experimentation, and logical reasoning. Two philosophers stand out in its development, Francis Bacon and René Descartes. Bacon championed inductive reasoning, the process of deriving general principles from specific observations. He encouraged a method grounded in data collection, experimentation, and empirical validation. In contrast, Descartes emphasized deductive reasoning, arguing that truth must be built on a foundation of clear, methodical logic rooted in mathematical certainty. Although their approaches differed, Bacon and Descartes shared a common goal: to establish a reliable method for acquiring knowledge. Their philosophies eventually converged into a cohesive framework that blended induction and deduction with rigorous experimentation. This framework would reach a new level of sophistication with the work of Isaac Newton. His monumental Philosophiae Naturalis Principia Mathematica, commonly known as the Principia, synthesized the findings of his predecessors into a unified theory of motion and gravitation. Using mathematical formulas and empirical testing, Newton demonstrated that the universe operated according to consistent and discoverable laws. By the late 17th century, the scientific community had begun to adopt a standardized approach to inquiry. Formulate a hypothesis, test it through repeatable experiments, observe the outcomes, and draw conclusions based on evidence. This process encouraged collaboration, peer review, and a cumulative growth of knowledge that stood in stark contrast to the isolation and rigidity of medieval scholasticism. The scientific method marked more than just a new way of thinking. It represented a monumental shift in how humanity understood its place in the cosmos. No longer was knowledge passed down as immutable truth. It was now something to be questioned, tested, and improved upon. And this method, this structured search for understanding, did not stop with Earth. Space exploration, arguably the most audacious extension of the scientific method, opened a gateway to the stars. Starting in the mid-20th century, the launch of artificial satellites and the first crewed missions heralded a new era. Humans, for the first time, broke free from Earth's atmosphere and looked back at our pale blue planet with fresh eyes. This technological leap allowed us to study celestial phenomena with a clarity never before possible. From observing the rings of Saturn to detecting exoplanets orbiting distant stars, our ability to collect data from the cosmos expanded exponentially. Instruments aboard space telescopes, probes, and rovers began revealing secrets about the solar system and beyond, secrets that had remained hidden for billions of years. The pursuit that began in the quiet libraries of Renaissance Europe now stretches across galaxies, and yet the core principle remains the same: ask questions, seek evidence, and never stop exploring. And so began one of humanity's most defining chapters, the Apollo missions. At the height of geopolitical tension and scientific ambition, humans landed on the moon, marking a turning point not just in history, but in our understanding of the universe. These missions were more than symbolic victories of exploration. They were scientific triumphs that opened the lunar surface to direct human study for the first time. The astronauts didn't just leave footprints, they brought back priceless cargo, rocks and soil that would transform our knowledge of the moon's geological history. These samples revealed stories billions of years old. Encoded in dust and stone, they painted a picture of a once molten world, a silent witness to the formation of our solar system. With every grain of lunar regolith examined under Earth's microscopes, scientists found themselves facing deeper and more profound questions. How did planetary bodies form? What forces shaped their evolution? Could the conditions for life exist beyond Earth? Fueled by the success of the Apollo and Soviet Luna programs, space agencies turned their eyes outward. The moon was just the beginning. Robotic spacecraft became our emissaries to the outer planets. With missions like Voyager, Galileo, and Cassini, humanity's presence extended far beyond Earth's orbit, diving deep into the cold reaches of the solar system. Voyager, still traveling into interstellar space, revealed the swirling storms of Jupiter, the shimmering rings of Saturn, and the textured moons that danced around them. Galileo unveiled volcanic activity on Io and hinted at a subsurface ocean beneath Europa's icy crust. Cassini confirmed geysers spraying water vapor from Enceladus, launching particles into space from a hidden sea beneath its frozen shell. Each of these discoveries suggested something remarkable, that the ingredients for life might exist in the most unexpected corners of our solar system. But the journey didn't stop with robotic scouts. As telescopes evolved, so too did our perspective on the universe itself. Advanced ground-based observatories and space telescopes revolutionized astronomy. Chief among them was the Hubble Space Telescope, a sentinel floating above Earth's atmosphere, capturing the cosmos in unprecedented detail. Through Hubble's lens, humanity witnessed the birth and death of stars, the collision of galaxies, and the quiet drift of distant nebulae. It allowed us to peer back in time to see galaxies as they were billions of years ago. Crucially, Hubble and its successors enabled the detection of exoplanets, worlds orbiting stars light years away. Some of these alien planets reside in what astronomers call the habitable zone, where liquid water could exist. Each new discovery reshaped our understanding of planetary systems and forced us to reconsider what environments might support life. The exploration of space hasn't just answered old questions, it's raised new ones. It's taught us that to understand our present, we must study the past, particularly the origins of the universe itself. Observing the early universe requires more than powerful optics. It requires technologies capable of capturing the faintest whispers of light and energy from across cosmic time. Space telescopes, free from atmospheric distortion, are critical tools in this endeavor. Instruments like Hubble operate across a broad range of wavelengths, from ultraviolet to infrared, allowing scientists to decode the light of ancient galaxies. These observations tell us how galaxies formed, how they evolved, and what forces shaped them over billions of years. Another cornerstone of cosmology is radio astronomy. This technique allows scientists to detect the cosmic microwave background radiation, faint, ancient signals that date back to the Big Bang. This radiation is the universe's oldest light, and it holds clues to its composition, early temperature variations, and the accelerating expansion of space itself. Facilities like the Atacama Large Millimeter Submillimeter Array have become essential in deciphering this relic radiation, helping researchers build a clearer map of the universe's infancy. Perhaps one of the most vital tools in the astronomer's arsenal is spectroscopy. By splitting light into its component wavelengths, scientists can analyze the signatures of elements within stars, galaxies, and interstellar clouds. This technique allows us to determine the temperature, motion, and chemical makeup of celestial bodies, from the nearest stars to the furthest galaxies. Through spectroscopy, astronomers have traced the origin of the elements themselves, following their evolution from the primordial soup of the early universe to the formation of stars, planets, and eventually life. In the grand narrative of space exploration, each mission, each breakthrough is a paragraph in a story that continues to unfold. Our understanding of celestial mechanics, cosmic structures, and the very nature of space and time is constantly being rewritten. As we gaze further into the cosmos, we are reminded that the universe is not a static backdrop, but a dynamic, ever-changing expanse, alive with history, mystery, and possibility. And lastly, in the grand chronicle of cosmic exploration, the rapid evolution of computational technology has emerged as one of the most transformative forces in our understanding of the universe. No longer confined to abstract equations or limited observations, scientists now harness high-performance computing to unlock the very fabric of cosmic evolution. In sprawling data centers and specialized research facilities across the globe, machines hum with intensity, running simulations that attempt to mirror the grandeur of the cosmos. These aren't mere animations. They are detailed, mathematically driven recreations of galactic collisions, star births, and the mysterious ebb and flow of dark matter across space-time. Thanks to advances in computational power, what was once invisible or incomprehensible can now be rendered into high-fidelity models, opening windows into the distant past of the universe. Imagine, for a moment, trying to trace the formation of an entire galaxy, from a chaotic cloud of gas to a majestic spiral of stars, using nothing but pen and paper. For decades, this was the limit of theoretical astrophysics. Today, however, powerful supercomputers equipped with thousands of interconnected processors perform these calculations in a fraction of the time, running simulations across billions of virtual years. This allows scientists to test hypotheses with unprecedented depth, comparing theoretical predictions with real-world observations from telescopes and space missions. And yet, it's not just about computing speed. The complexity of these models has grown enormously. Researchers now create three-dimensional simulations that capture the gravitational ballet of entire galaxy clusters. These virtual universes reveal patterns of motion, matter distribution, and cosmic web structures that are vital to understanding the large-scale architecture of the cosmos. In this digital cosmos, artificial intelligence has taken its place not as a mere assistant, but as a co-investigator in the search for truth. Machine learning algorithms, trained on vast repositories of data, now help identify subtle patterns buried within torrents of astronomical information. With telescopes capturing images of billions of galaxies, the scale of data is staggering, far beyond human capacity to analyze manually. AI sifts through this deluge like recognizing phenomena that might otherwise be missed and suggesting new avenues for exploration. Moreover, artificial intelligence doesn't stop at analysis. It contributes directly to the creation of simulations themselves. Advanced neural networks help refine the accuracy of models by incorporating new data continuously, making them more predictive and reflective of the real universe. Whether it's simulating the turbulent dynamics of a collapsing star or the gravitational warping caused by dark matter, AI plays a crucial role in revealing the invisible mechanics of the cosmos. These computational tools have also bridged the long-standing divide between theory and observation. Thanks to the rise of big data techniques, astronomers now merge empirical findings with theoretical simulations, achieving a synthesis that was previously unthinkable. Data from observatories such as the James Webb Space Telescope or the Vera C. Rubin Observatory can now be directly integrated into models, sharpening the precision of our cosmic forecasts. As computer technology advances, so too does our capacity to probe deeper, further, and with greater clarity. Each leap in hardware capability or algorithmic sophistication pushes the boundaries of what we know about the universe. The story of the cosmos, from the first microsecond after the Big Bang to the formation of galaxies and beyond, is being rewritten in real time, powered by the relentless pulse of computation. We are no longer mere spectators of the universe. Through simulations, models, and artificial intelligence, we are active participants in uncovering its secrets. The mysteries of dark matter, dark energy, and cosmic inflation are no longer confined to chalkboards or speculation. They are becoming, through the lens of technology, visible, testable, and perhaps one day fully understood. In this new era of cosmology, shaped by silicon and code, we stand at the edge of something profound. The machine and the mind working in concert are bringing us closer than ever to answering the most ancient of questions. How did this all begin? And where, in the vast sweep of space and time, are we headed? Moreover, machine learning techniques have revolutionized the way astronomers classify celestial objects, transforming a once painstaking process into an automated and highly efficient operation. For example, artificial intelligence systems can now rapidly distinguish between different types of supernova or detect exoplanets orbiting distant star systems with remarkable speed and accuracy. This leap in capability not only accelerates the pace of astronomical discoveries, but also frees scientists from the time-consuming task of sifting through massive amounts of data, allowing them to focus more on interpreting findings and generating new hypotheses. Artificial intelligence is also paving the way for groundbreaking theories in cosmology. By utilizing unsupervised learning methods, researchers can identify hidden patterns and unexpected relationships within vast, complex data sets. These insights have the potential to reveal new physical principles or previously unknown cosmic phenomena. As computing power continues to advance and datasets grow exponentially, the collaboration between AI and cosmology promises to uncover even more of the universe's secrets that remain hidden today. Turning to the cosmos itself, the observable universe presents an intricate tapestry woven from several key components. At its core, dark energy dominates, making up roughly 70% of the universe. This mysterious force is believed to be responsible for driving the accelerated expansion of the cosmos. Despite its immense influence, the true nature of dark energy remains one of the greatest unsolved puzzles in cosmology, profoundly shaping both the structure and ultimate fate of the universe. Following dark energy, dark matter accounts for approximately 25% of the universe's total makeup. Unlike ordinary matter, dark matter neither emits, absorbs, nor reflects light, making it invisible to conventional telescopes. However, its presence is detected through its gravitational effects, which influence the motion of galaxies and clusters of galaxies. This unseen mass acts like cosmic glue, holding galaxies together and helping to shape large-scale cosmic structures. While the exact particles that compose dark matter are still unknown, ongoing research continues to explore this invisible force's role in the universe. Ordinary or baryonic matter constitutes just about 5% of the universe. This familiar matter includes everything we can observe directly, from stars and planets to gas and dust. Though it represents a minor fraction of the cosmic mass-energy budget, baryonic matter is the building block of galaxies, celestial bodies, and life itself. This form of matter is distributed unevenly across the cosmos, creating the rich variety of structures that captivate astronomers and cosmologists alike. The study of the universe's composition is an ongoing journey. Advances in telescope technology and experiments designed to detect dark matter and dark energy continually refine our understanding. Scientists are piecing together this cosmic puzzle, gradually revealing the fundamental nature of the universe and the intricate dance between its mysterious components. One crucial aspect of understanding the cosmos is measuring its expansion, quantified by a value known as the Hubble constant. This constant describes the speed at which galaxies move away from each other depending on their distance. Current estimates suggest that galaxies recede at a rate of about 70 kilometers per second for every 3.2 million light-years of distance. This means that the farther a galaxy is from us, the faster it appears to be moving away. This rapid expansion points to a universe that has been growing ever since its birth in the Big Bang, which occurred roughly 13.8 billion years ago. More intriguingly, the current rate of expansion is not constant, but accelerating, a phenomenon attributed to dark energy. This mysterious force seems to counteract gravity, pushing galaxies apart and reshaping our understanding of the cosmos. The discovery of this accelerating expansion has profound implications. It suggests the existence of forces and cosmic components that scientists have yet to fully grasp. Moreover, it raises fundamental questions about the universe's ultimate fate. If the expansion continues to speed up, one possible outcome is that galaxies will eventually drift so far apart that the observable universe becomes an isolated collection of stars and galaxies, leading to a scenario known as the Big Freeze, where cosmic structures grow cold and dark over unimaginable timescales. In this vast cosmic story, artificial intelligence, dark energy, dark matter, and the accelerating expansion of the universe all play pivotal roles. Together, they weave a narrative that challenges our understanding, inviting humanity to explore deeper into the mysteries of existence itself. However, if the universe's expansion were to slow down, it could lead to dramatically different outcomes, such as an eventual gravitational collapse. Understanding the rate at which the universe expands is not just a glimpse into its distant past, it is also a vital window into what lies ahead. As scientists strive to refine the measurements of the Hubble constant, the number that tells us how fast the universe is expanding, and improve our understanding of dark energy, we move steadily closer to unlocking the fundamental principles that govern everything in the cosmos. Each new discovery in this field brings us closer to unraveling some of the deepest mysteries of existence itself. One of the most significant pieces of evidence supporting the Big Bang Theory is the cosmic microwave background, a faint glow of radiation that fills the entire universe. This radiation is essentially the afterglow of the universe's hot and dense state shortly after its birth. Around 380,000 years after the Big Bang, the universe had expanded and cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This event allowed light to travel freely through space for the very first time. As the universe continued to expand, this primordial light shifted from the visible spectrum into the microwave range, a phenomenon known as redshift. Today we detect it as a remarkably uniform background radiation with a temperature of about 2.7 degrees above absolute zero. The astonishing consistency of this radiation across the sky holds a treasure trove of information about the early universe, revealing critical details about its origins, composition, and evolution. Scientists closely analyze the tiny fluctuations in temperature and density found within this cosmic microwave background. These minute variations represent the primordial density fluctuations from which galaxies and vast cosmic structures eventually formed. By studying these irregularities, researchers gain valuable insights into the composition of the early universe, including the proportions of ordinary matter, and dark energy. This detailed analysis also allows scientists to estimate important cosmological parameters such as the age of the universe and its expansion rate. The cosmic microwave background serves as a remarkable cosmic fossil, offering us a snapshot of the universe at a very formative stage. With each advancement in telescopes and observational instruments, we gain greater precision in studying these ancient signals. Every new finding not only deepens our understanding of the universe's early conditions, but also helps test and refine our current models of cosmology, enabling us to piece together the grand story of cosmic evolution. Moving from the earliest times to the large-scale structures in the universe, galaxy clusters stand out as vast groupings of galaxies held together by gravity. These clusters can contain hundreds or even thousands of individual galaxies and are the largest gravitationally bound structures in the cosmos, often spanning millions of light years. Beyond galaxies themselves, these clusters also contain dark matter, hot gas, and sometimes supermassive black holes at their centers. Understanding galaxy clusters is vital because they act as natural laboratories for studying the fundamental forces and processes shaping the universe. These clusters form through a process called hierarchical clustering, where smaller groups of galaxies merge over cosmic time to build larger structures. This process began with tiny fluctuations in the density of matter in the early universe, driven by gravitational instabilities that attracted gas and dark matter into dense regions called protoclusters. Over billions of years, these protoclusters accumulated more matter and merged with other groups to become the enormous galaxy clusters we observe today. Inside these clusters, gravitational interactions play a crucial role. When galaxies collide and merge, these encounters can trigger intense bursts of star formation, creating new stars from the gas available. But it is not just the galaxies themselves that are important. The hot gas present in clusters, which can reach temperatures of millions of degrees, plays a key role in the cluster's overall dynamics and evolution. This gas emits X-rays, which astronomers use to gain vital information about the cluster's mass and composition. Galaxy clusters are also fundamental to our understanding of dark matter and dark energy. By studying how galaxies move and interact within these clusters, scientists can infer the distribution of dark matter. a mysterious form of matter that does not emit, absorb, or reflect light, but makes up about 1/4 of the universe. Additionally, the behavior of galaxy clusters helps researchers understand the rate of cosmic expansion, offering clues about dark energy, the unknown force driving the accelerated expansion of the universe. The existence of dark matter and dark energy has been deduced from many observations that ordinary matter alone cannot explain. One of the most compelling pieces of evidence for dark matter comes from studying the rotational speeds of galaxies. Observations show that galaxies spin so rapidly that if they were made only of visible matter, they would tear themselves apart. Instead, they remain intact, implying the presence of an invisible mass, dark matter, holding them together. In this way, galaxy clusters and the cosmic microwave background provide us with critical windows into the past, present, and future of the universe. They illuminate the intricate web of cosmic evolution and bring us ever closer to answering the fundamental questions about our existence and the universe we call home. However, the presence of unseen mass, known as dark matter, provides the crucial gravitational force needed to hold galaxies together. Without this invisible substance, the stars and galaxies would fly apart due to insufficient gravity. This unseen mass acts like an invisible glue, stabilizing galaxies and ensuring their structure remains intact. Another powerful piece of evidence for dark matter comes from studying clusters of galaxies. Astronomers examine these massive groups by measuring their total mass, using several techniques. One method involves analyzing the motion of the individual galaxies within the cluster. These galaxies move as if influenced by a much larger mass than what we can see. Additionally, clusters contain extremely hot gas that emits X-rays, and measuring this radiation helps estimate the cluster's total mass. The results from these measurements consistently reveal a mass far greater than what is visible, again hinting at a mysterious dark matter presence. Gravitational lensing offers yet another remarkable window into the dark universe. This phenomenon occurs when light from very distant objects bends around a massive galaxy cluster on its way to Earth. By carefully mapping this bending of light, astronomers can trace the distribution of mass, including dark matter, in and around these clusters. The strength of the lensing effect often points to large amounts of hidden mass enveloping galaxies, mass that cannot be accounted for by ordinary matter alone. On the other side of the cosmic puzzle lies dark energy, an even more mysterious force thought to make up about 70% of the entire universe. Dark energy is primarily known through the observation that the universe's expansion is accelerating. In 1998, astronomers studying supernova, exploding stars that serve as standard candles for measuring cosmic distances, made a startling discovery. These supernovae appeared dimmer and farther away than expected, suggesting that the universe is not just expanding, but doing so at an ever-increasing pace. This accelerated expansion is driven by a repulsive force attributed to dark energy. Further clues about dark energy come from the cosmic microwave background, the faint afterglow of the Big Bang. Observations of this ancient light reveal that the overall shape or geometry of the universe is flat. This flatness aligns well with a cosmos dominated by dark energy. Moreover, when astronomers observe the large-scale structures and the distribution of galaxies across vast cosmic distances, they find patterns that support the idea that dark energy plays a vital role in shaping the universe's evolution. Together, these observations provide some of the most compelling evidence for both dark matter and dark energy, two invisible components that dominate the cosmos. Despite their profound influence, their exact nature remains one of the greatest mysteries in modern physics. Measuring distances across the universe is no simple task. The scales involved are immense, spanning millions or even billions of light years. To tackle this challenge, astronomers use a series of interconnected techniques known as distance ladders. Each rung of this ladder builds on the previous one, covering different distance ranges to provide a comprehensive picture. The most fundamental technique is called parallax. This method involves observing nearby stars from two different points in Earth's orbit around the Sun. By measuring the tiny apparent shift in a star's position against the background of more distant stars, astronomers can use basic trigonometry to calculate its distance. However, parallax works only for relatively close stars, generally within a few hundred light years. For more distant objects, astronomers rely on standard candles, celestial objects with known intrinsic brightness. One key example is the type Ia supernova, a specific kind of exploding star with a consistent peak brightness. When a type 1a supernova occurs in a faraway galaxy, astronomers compare its observed brightness to its true brightness, allowing them to determine how far away it is. This method is crucial for measuring distances to galaxies millions of light years away. Another technique, called the Tully-Fisher relation, uses properties of nearby galaxies, such as their mass and luminosity or the motion of their constituent stars, to estimate distances to even farther galaxies. This method extends the reach of astronomers while maintaining reliable accuracy. As distances grow ever larger, redshift becomes essential for mapping the cosmos. Redshift is the phenomenon where light from distant galaxies shifts toward longer wavelengths, indicating these galaxies are moving away from us. The greater the redshift, the faster a galaxy is receding, a direct result of the universe's expansion. By combining redshift data with Hubble's law, which links redshift to distance, astronomers can estimate how far these distant galaxies lie from Earth. Together, these methods form a robust and interconnected framework, allowing scientists to measure cosmic distances with remarkable precision. This intricate ladder of measurements enriches our understanding of the universe's vast structure and composition, revealing a cosmos far more complex and mysterious than once imagined. The nature of dark matter stands as one of the deepest and most captivating mysteries in modern astrophysics. This invisible substance makes up about 1/4 of the total mass-energy content of the universe, yet it stubbornly evades direct detection. Unlike ordinary matter, which interacts with electromagnetic forces and can be seen because it emits, absorbs, or reflects light, dark matter remains completely dark. It does not interact with light at all, making it impossible to observe through traditional astronomical techniques that depend on detecting light. Instead, scientists have uncovered the presence of dark matter through its gravitational influence on visible objects as galaxies, and clusters of galaxies, as well as its role in shaping the large-scale structure of the cosmos. Among the leading hypotheses to explain what dark matter might be, the most popular suggests it consists of weakly interacting massive particles, or WIMPs. These particles are thought to have mass and to interact gravitationally, but only weakly with ordinary matter through other forces, making them extremely elusive. WIMPs have been a prime target for decades of experiments designed to catch a direct glimpse of them here on Earth, but so far none of these attempts have produced conclusive evidence. Another fascinating candidate for dark matter is the axion, a hypothetical, extremely light elementary particle. Like WIMPs, axions would interact only weakly with ordinary matter and would require indirect detection methods. Scientists are exploring ways to observe axions by looking for subtle effects they might produce in high-energy processes or in the early universe. Some researchers even propose that dark matter may not be a particle at all. Instead, the mystery could be rooted in our understanding of gravity itself. Theories such as modified Newtonian dynamics suggest that what we attribute to dark matter might actually arise from changes in gravitational laws at very large distances. While this idea challenges conventional physics, it emphasizes how crucial it is to fully understand both dark matter and the fundamental forces shaping the universe. Despite these efforts, the true nature of dark matter remains hidden, a cosmic secret waiting to be unraveled. Ongoing experiments in particle physics and astrophysics are essential to cracking this puzzle. Each new discovery brings us closer to a fuller picture of the universe, and as scientists continue their investigations, they may reveal profound truths about the very fabric of reality. Alongside the mystery of dark matter, the universe's accelerated expansion presents another cosmic puzzle, one attributed to an enigmatic force known as dark energy. This force was discovered in 1998 when astronomers observed distant exploding stars called supernovae and found that the universe's expansion was speeding up rather than slowing down. Dark energy is believed to make up about 70% of the total energy content of the universe, but what it actually is remains one of the biggest questions in cosmology. One leading idea is that dark energy might be a constant energy density permeating space uniformly, known as the cosmological constant. This concept dates back to Albert Einstein, who introduced it in his equations of general relativity to maintain a static universe. When the expansion of the universe was discovered, he called this his greatest blunder. But the idea regained importance after the discovery of cosmic acceleration decades later. Another possibility is that dark energy is dynamic and changes over time or varies across space. Some theories describe it as quintessence, a field somewhat like a scalar field, which could evolve and have behaved differently in the early universe than it does today. This dynamism could have played a key role in shaping the evolution of the cosmos. The effects of dark energy are vast and far-reaching. If the acceleration of the universe's expansion continues indefinitely, the ultimate fate of the cosmos could be a chilling, big freeze. In this scenario, galaxies would drift ever farther apart, stars would burn out, and the universe would become cold and isolated, dominated by dark energy's relentless influence. This paints a picture of a future very different from the bustling, star-filled universe we know today. To unravel the mystery of dark energy, scientists employ a variety of observational tools. They study the cosmic microwave background, the faint glow left over from the Big Bang, and examine the large-scale structure of the universe to gather data on how dark energy shapes cosmic expansion. Each new piece of evidence helps refine our understanding of the forces driving this accelerated expansion, bringing us ever closer to grasping the true nature of the universe. Beyond dark matter and dark energy lies a realm of even more speculative ideas, such as the concept of the multiverse. This idea proposes that our universe is just one among many, possibly an infinite collection of universes making up everything that exists. While the multiverse concept sparks the imagination and finds some support in theoretical frameworks, it remains highly speculative and, so far, lacks direct empirical evidence. For now, the multiverse remains a fascinating hypothesis at the frontier of cosmological thought, inviting us to imagine the vast possibilities that might lie beyond our cosmic horizon. One of the most influential and widely discussed theories proposing the existence of a multiverse emerges from the concept of cosmic inflation. Cosmic inflation refers to the extraordinary and rapid expansion of the universe that occurred in the fleeting moments immediately following the Big Bang. According to certain inflationary models, this exponential growth did not unfold uniformly across all regions of space. Instead, some areas ceased their inflationary expansion earlier than others, potentially giving rise to what scientists call pocket or bubble universes. Each of these bubbles could possess distinct physical properties and fundamental constants, effectively creating a vast and diverse landscape of universes, each with its own unique characteristics. In this fascinating framework, the universe we observe, the one encompassing everything we know, is just one bubble amid an enormous multiverse filled with countless other universes, each isolated and potentially very different. The idea radically expands our cosmic perspective, inviting us to imagine an almost infinite array of realities existing alongside our own. Another prominent theoretical approach predicting the existence of multiple universes comes from string theory, a bold attempt to unify all the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces into a single coherent framework. String theory posits that the fundamental building blocks of reality are not point-like particles, but rather tiny, vibrating strings. Remarkably, it also suggests that the universe contains additional spatial dimensions beyond the three we experience daily, as well as the one dimension of time. The shape and configuration of these extra dimensions, often curled up or compactified in intricate ways, could give rise to an immense variety of possible universes, each with its own set of physical laws. This creates a staggering landscape of possible realities, where the rules governing particles, forces, and the fabric of space-time might differ dramatically from those in our own universe. Despite the mathematical elegance and intellectual appeal of these ideas, the existence of other universes remains a deeply contested and speculative topic in modern science. While theoretical models provide plausible frameworks, direct observational evidence is exceedingly difficult to obtain. Our telescopes and instruments are limited to studying the universe visible to us and the realms beyond. Even if they exist, remain hidden behind insurmountable cosmic horizons. This challenge raises profound philosophical questions about the nature of reality and our place within it. What does it mean if our universe is just one of countless others? How does that reshape our understanding of existence and the laws that govern it? These questions stretch beyond physics, touching on the very essence of what it means to be part of the cosmos. The concept of a multiverse continues to captivate scientists, philosophers, and the public alike, serving as fertile ground for theoretical research and imaginative exploration. As our understanding of physics and cosmology deepens, new insights may one day emerge to either confirm or disprove the existence of these parallel universes, thereby enriching our comprehension of the cosmos as a whole. Turning to an even more fundamental mystery, the question of what preceded the Big Bang. The event that marks the beginning of time and space as we understand them invites both scientific inquiry and philosophical reflection. According to the prevailing cosmological model, the universe began as an extraordinarily hot and dense point, which then expanded rapidly, creating space and time themselves. This presents a paradox when we try to consider what came before the Big Bang, since time itself is thought to have started at that moment. Some scientists argue that the notion of before the Big Bang may be meaningless within our current understanding of physics, as time is inherently tied to the fabric of the universe that emerged from the Big Bang. Moreover, the equations of general relativity, which describe how gravity shapes the curvature of space-time, break down under the extreme conditions near the Big Bang, where density and curvature approach infinity. This singularity suggests that conventional concepts of time and space do not apply in the way we expect. To address this dilemma, several theories have been proposed. One such idea is the cyclical universe model, which suggests that the cosmos undergoes endless cycles of expansion, Big Bang, and contraction, Big Crunch. In this view, our current universe is just one in an eternal sequence, where each Big Bang arises from the collapse of the previous universe, creating a never-ending cosmic rhythm. Another intriguing approach comes from quantum gravity, a field aiming to reconcile general relativity with quantum mechanics. Some models within this framework propose that the Big Bang was born from quantum fluctuations in a pre-existing state or realm, bypassing the classical limitations of time and space. This could mean the universe evolved from conditions beyond our current comprehension, potentially redefining the origin of reality itself. While these theories offer captivating possibilities, none have been definitively proven due to the absence of observational evidence from before the Big Bang. The quest to understand the true origins of the universe remains one of the most profound scientific challenges. Finally, one of the greatest puzzles in cosmology and particle physics concerns the asymmetry between matter and antimatter. According to current theories, the Big Bang should have produced equal amounts of both matter and antimatter. Antimatter consists of particles that mirror ordinary matter, but with opposite charges and properties. For example, the electron's counterpart, the positron. If matter and antimatter had existed in perfect balance, they would have annihilated each other completely upon contact, leaving behind a universe filled only with radiation. Yet, the observable universe is overwhelmingly dominated by matter, enabling the formation of stars, planets, and ultimately life itself. Understanding why this imbalance exists remains one of the most perplexing and critical questions driving modern research into the fundamental nature of the cosmos. Several hypotheses strive to unravel one of the greatest mysteries of our cosmos. Why is our universe overwhelmingly composed of matter rather than antimatter? Among these, one leading concept is known as biogenesis. This theory suggests that in the earliest moments after the Big Bang, certain physical processes tipped the scales, favoring the creation of baryons, the particles that make up normal matter, over their antimatter counterparts, known as antibaryons. To understand this imbalance, scientists look to conditions that prevailed in the early universe, where unique interactions might have taken place. One key phenomenon thought to play a role is called CP violation. This refers to a subtle asymmetry in the laws of physics where particles and antiparticles behave differently under certain conditions, Such a violation could have caused a tiny excess of matter to emerge during the intense, high-energy collisions that occurred shortly after the birth of the universe. Another intriguing angle comes from the idea of lepton asymmetry. Leptons are a different class of fundamental particles, which include electrons and neutrinos. This theory proposes that interactions involving leptons, especially neutrinos and their antiparticles, might have contributed to the matter-antimatter imbalance by creating an excess of matter. Researchers continue to explore this possibility through experiments in powerful particle colliders and observations of astrophysical phenomena, searching for clues hidden in the fabric of the cosmos. Despite the progress made, the precise mechanism that caused the universe to favor matter remains elusive. Solving this puzzle is vital, not only for understanding how our universe evolved, but also for revealing deeper truths about the fundamental laws of physics. Every new piece of data gathered from experiments, whether smashing particles at near-light speeds or peering deep into space, brings us closer to answering why we exist in a universe dominated by matter. Equally captivating is the question of the ultimate fate of black holes, those mysterious cosmic objects formed from the remnants of massive stars after they have exhausted their nuclear fuel. Black holes possess gravitational fields so intense that nothing, not even light, can escape their grasp. Yet their destiny is far more complex than simply swallowing everything in their path. One influential theory about black holes' fate comes from the work of physicist Stephen Hawking, who proposed a process now called Hawking radiation. According to this idea, black holes are not entirely black. Instead, quantum mechanical effects near their event horizons cause them to emit tiny amounts of thermal radiation. Over unimaginably long periods, this radiation slowly causes black holes to lose mass. If this process continues uninterrupted, black holes could eventually evaporate completely. For black holes with masses similar to stars, this evaporation takes an incredibly long time, much longer than the current age of the universe. Supermassive black holes, which can contain millions or even billions of times the mass of our Sun, lose mass through Hawking radiation at a glacial pace. Meanwhile, as the universe expands and changes, the environment around these black holes will also evolve, potentially influencing how quickly they lose mass. Another factor in the fate of black holes is their tendency to merge. As black holes interact gravitationally with nearby matter and other black holes, they can grow larger, creating giants that may eventually succumb to the slow process of Hawking radiation. Still, these transformations take place on timescales that dwarf human history by unfathomable amounts. The ultimate destiny of black holes raises profound questions about the future of the universe itself. As the cosmos continues to expand and age, black holes could significantly shape the evolution of galaxies and the large-scale structure of the universe. Though much remains unknown, each discovery deepens our understanding of these enigmatic objects at the heart of modern astrophysics. Turning our gaze to the fate of the universe as a whole, cosmologists and philosophers have long debated how everything might end. Several compelling theories paint different pictures of the cosmos's final act, shaped by factors like dark energy, matter density, and the universe's geometry. Among the most discussed scenarios are the Big Freeze, the Big Crunch, and the Big Rip. The Big Freeze, sometimes called heat death, is currently the most favored explanation based on observations of the universe's accelerating expansion. In this scenario, dark energy pushes galaxies farther and farther apart, causing the universe to expand forever. Over unimaginable eons, stars will burn out, galaxies will drift away from one another, and the cosmos will become cold and dark. Eventually, black holes will evaporate through Hawking radiation, leaving behind only scattered particles in an immense, empty void. Temperatures will approach absolute zero, and all organized structures will dissolve into chaos. Other possibilities, such as the Big Crunch, where the universe might someday stop expanding and collapse back on itself, or the Big Rip, where the expansion accelerates so violently that it tears apart galaxies, stars, and even atoms, remain under investigation. Each theory presents a profound vision of the universe's destiny, reflecting our ongoing quest to understand the cosmos from its fiery beginnings to its ultimate end. In exploring these grand questions, scientists continue to push the boundaries of knowledge using ever more powerful tools and creative thinking. Each new insight illuminates our place in this vast, mysterious universe and brings us closer to understanding the forces that shaped everything we see and everything we are. Conversely, the Big Crunch theory suggests a fascinating possibility. The universe's current expansion might one day reverse if the overall density of matter surpasses a certain critical threshold. In such a scenario, gravity, the force that binds everything together, would gradually pull all matter back toward a single point. Galaxies, stars, and planets would begin to collapse inward, converging toward an unimaginably dense singularity. This state would resemble the extreme conditions thought to exist at the very beginning of the universe, just after the Big Bang. As everything compacts, temperatures and densities would skyrocket, potentially igniting a new fiery phase. Some scientists speculate this collapse might lead to another Big Bang, thus creating an endless cosmic cycle of expansion and contraction, a universe eternally breathing in and out. On the other hand, the Big Rip presents a far more dramatic and unsettling fate. Instead of slowing or reversing, the universe's expansion would accelerate without limits, driven by a mysterious, ever-strengthening form of dark energy. This relentless acceleration would eventually tear apart galaxies, breaking the bonds that hold stars and planets together. As time progresses, even solar systems would disintegrate, and ultimately, the very atoms that compose matter would be ripped apart. The scale of this timeline spans unimaginable lengths of time, but the outcome would be a violent and total destruction of everything in existence. These two theories are among the most widely discussed, yet they are far from the only possibilities. Some cosmologists propose ideas such as the multiverse, a vast and intricate ecosystem where our universe might be just one of countless others, each with its own birth, evolution, and fate. These diverse scenarios challenge and expand our understanding of reality, probing the very essence of cosmic evolution and the fundamental laws that govern existence. While the ultimate destiny of the cosmos remains unknown, ongoing research in cosmology continues to peel back the layers of this grand mystery, revealing new insights into the complex possibilities that await. Shifting focus to the birth of stars, this process is intricately tied to the availability of gas and dust, primarily hydrogen and helium, the universe's most abundant elements. Star formation is still actively occurring today, especially within dense regions known as stellar nurseries or molecular clouds, where these raw materials are plentiful. However, the rate at which new stars form is gradually declining over cosmic time. As the universe expands and matter becomes more spread out, the density of gas necessary for star formation decreases, making it harder for clouds to collapse under gravity to ignite new stars. Moreover, as stars age and die, they use up available material and enrich space with heavier elements forged in their cores. Massive stars explode as supernovae, scattering these elements back into the cosmos. Yet despite this recycling, the overall gas reservoir is slowly depleting. Current models estimate that star formation will continue for tens of billions of years, but will steadily taper off. Early in cosmic history, just a few billion years after the Big Bang, star formation rates were much higher, with numerous massive stars lighting up the young universe. Over time, as the cosmic fuel runs low, star formation will slow to a trickle, eventually becoming exceedingly rare. Scientists predict that in around 100 trillion years, star formation might cease entirely, ushering in a state known as stellar dormancy. The universe at that point will be a far quieter, dimmer place. Most stars will have aged or died, leaving behind a sparse population of smaller, longer-lived stars and brown dwarfs. Any new stars born in this distant future would likely be smaller and formed under drastically altered conditions compared to today's universe. Understanding these timescales and the star formation process is essential. It offers a window into the evolution of galaxies and the broader cosmic ecosystem that gave rise to the stars we admire in the night sky. Looking ahead to a more immediate cosmic event, the impending collision between our Milky Way galaxy and the neighboring Andromeda galaxy stands as one of the most monumental events in cosmic terms. This encounter is expected to unfold in roughly 4 billion years and is a natural part of galactic evolution driven by gravity's pull. Andromeda is currently moving toward the Milky Way at about 110 kilometers per second on a direct collision course. As these two vast systems draw near, they will not collide in a fiery smash, as one might imagine. Galaxies are mostly empty space, so actual star-to-star collisions are incredibly unlikely. Instead, their mutual gravitational forces will distort their shapes, causing spectacular tidal interactions. The compression of gas and dust during these interactions will ignite bursts of star formation, as dense pockets collapse into new stars amid the chaos. This cosmic dance will stretch over billions of years, culminating in the merger of the two galaxies into a single new entity. Scientists have coined playful names for this combined galaxy, such as Milkomita or Milkdruma. The merging process involves intricate gravitational interactions that will reshape the galaxies, potentially transforming them into a larger elliptical galaxy with complex internal structures. During this transformation, some stars will be flung out into intergalactic space, while others will find themselves orbiting newly formed central regions. The vast distances between stars mean actual collisions are rare, but the overall stellar environment will be forever changed. This grand cosmic event highlights the dynamic and ever-evolving nature of the universe, reminding us that even the stars and galaxies we see today are part of a much larger and ongoing story of change and transformation. However, the intricate interactions between galaxies will profoundly transform the dynamics and structure of the galaxies involved. The impending collision between our Milky Way and the Andromeda Galaxy presents an extraordinary cosmic event, a rare window into the complex processes of galaxy evolution and the grand life cycle of galaxies. As astronomers meticulously collect and analyze data on the movement, composition, and gravitational forces of both galaxies, they gain invaluable insights into how galaxies grow, merge, and reshape themselves over billions of years. This monumental cosmic dance, far from being merely destructive, represents a powerful chapter in the ongoing universal narrative. The collision will unfold over millions of years, gradually blending the stars, gas, and dark matter from both galaxies into a new, larger structure. This event will not only alter the shape and motion of stars within each galaxy, but will also trigger bursts of star formation as gas clouds collide and compress. Yet, despite the dramatic nature of this merger, it is just one act in the broader cosmic story, governed by fundamental forces that steer the universe on an immense scale. Among these forces, dark energy stands out as a central and mysterious player, shaping the long-term evolution of the cosmos. Comprising approximately 70% of the total energy content of the universe, dark energy drives the accelerated expansion of space itself. This phenomenon, observed through the increasing speed at which galaxies move apart, challenges our understanding of gravity and cosmic destiny. The most widely accepted explanation for dark energy is the cosmological constant, a term introduced by Einstein in his theory of general relativity. According to this concept, dark energy has a constant energy density that fills all of space evenly, exerting a repulsive force that counteracts the attractive pull of gravity. This tug-of-war causes galaxies to drift away from each other at an ever faster rate. As the universe continues to expand under the influence of dark energy, its effects will become increasingly pronounced. In the far future, star formation may slow significantly, and the light emitted by existing stars will gradually fade. The universe will grow colder and darker, entering what scientists call the Big Freeze, or heat death. Over trillions of years, galaxies will move so far apart that their light will no longer reach each other, and the formation of new stars will dwindle to near zero. The cosmos will become a vast, lonely expanse populated by cold remnants of stars and dark matter, devoid of the vibrant energy that once fueled celestial activity. Yet, dark energy may not be a static force. Some theories suggest it could change in strength or character over time and across different regions of space. If dark energy weakens, the universe's expansion could slow, possibly reversing into a cosmic contraction known as the Big Crunch, where all matter collapses back into a dense state. Conversely, if dark energy grows stronger, it could accelerate expansion to such extremes that it tears galaxies, solar systems, and even atoms apart in a cataclysmic event called the Big Rip. This profound uncertainty makes dark energy one of the most important subjects of modern cosmological research. By understanding its nature and effects, scientists hope to unlock the ultimate fate of the universe and the forces governing its grand evolution. Each new discovery reshapes our cosmic perspective, revealing the intricate balance of power and mystery that defines existence on the largest scales. The heat-death scenario, rooted in the second law of thermodynamics, predicts an inevitable decline into maximum entropy, a state where all energy is evenly dispersed and no useful work can be done. In this final cosmic chapter, stars will exhaust their nuclear fuel, becoming cold and dark remnants such as white dwarfs, neutrons, and black holes. Over unimaginable timescales, even black holes may evaporate through a process called Hawking radiation, slowly losing mass until they vanish entirely. This leads to a universe that is lifeless, static, and uniformly cold, an immense expanse with no temperature gradients or energy differences, incapable of supporting any form of dynamic activity or life. Despite the bleakness of heat death, it remains only one possible outcome. Ongoing research into dark energy and cosmic structure continues to refine our understanding, suggesting that the universe's future could be more complex and surprising than we currently imagine. One fascinating idea is the concept of cosmic rebirth, where the end of our universe could seed the beginning of a new one. In some theoretical models, the universe undergoes endless cycles of expansion and contraction in a process called the cyclic universe theory. After reaching a collapse phase resembling the Big Crunch, the universe might rebound in a new Big Bang, giving birth to a fresh cosmos with potentially different physical laws and constants. This cycle of death and rebirth could mean that the end of one universe naturally leads to the emergence of another. Another captivating possibility arises from quantum mechanics, where fluctuations in the quantum vacuum might spontaneously generate new universes. In this scenario, tiny bubbles of spacetime could form and rapidly expand, creating entirely separate universes with unique properties. This idea, known as the multiverse theory, suggests that countless universes may exist alongside our own, each with its own distinct realities and dimensions. Together, these ideas invite us to consider the universe not as a singular, isolated entity, but as part of a vast cosmic tapestry, woven from cycles, fluctuations, and unimaginable scales of time and space. The story of the cosmos is one of transformation and endless possibility, where each chapter reveals deeper mysteries and expands the horizon of human understanding. Additionally, theories connected to string theory suggest that the very fabric of the cosmos is far more intricate and multi-layered than our current understanding allows. In some extraordinary scenarios, entire regions of space might give rise to new physical realities, potentially creating multiple universes existing side by side. These ideas challenge our traditional concepts of time and space, introducing abstract and complex notions that stretch our comprehension well beyond the boundaries of the known universe. Yet, it is crucial to remember that these ideas remain largely theoretical. They have not been confirmed by direct observation or experimental evidence. While they offer fascinating glimpses into what the cosmos might be capable of, significant mysteries in fundamental physics persist. The true nature of time, gravity, and quantum mechanics continues to elude scientists. Only by resolving these deep questions can we determine whether a new universe could truly emerge from the remnants of an older one. As research in cosmology and theoretical physics moves forward, we edge closer to unlocking the universe's deepest secrets. We may one day uncover the links between the cosmic beginnings and possible cosmic endings, revealing how universes may be born, evolve, and perhaps fade away. Each new insight takes us further into understanding the complex tapestry of existence, weaving together the connections between multiple universes and the forces that shape them. Our grasp of cosmic history profoundly influences how we view humanity's place within this vast expanse. From the Big Bang to the formation of galaxies, stars, and planets, it becomes clear that humans are a very recent development in an ancient universe. This perspective invites both humbling realizations and profound existential questions. The universe is approximately 13.8 billion years old, with the first stars lighting up just a few 100 million years after the Big Bang. In stark contrast, human civilization has only existed for a few thousand years, barely a blink in cosmic time. This immense timeline can evoke feelings of insignificance, reminding us that human achievements and concerns are fleeting against the backdrop of such enormous spans. However, this cosmic chronology also highlights the astonishing conditions that allowed life and consciousness to emerge, the processes that lead to star and planet formation, and ultimately to life itself, are extraordinarily complex and rare. This means that although humanity might seem like a mere blip in the grand scheme, our existence is the result of countless finely balanced factors working in harmony. This rare confluence of circumstances inspires awe and underscores our unique role as conscious beings capable of not just living in, but also exploring and understanding the cosmos. Furthermore, understanding cosmic history deepens our appreciation for the interconnectedness of all matter in the universe. Essential elements for life, such as carbon and oxygen, are created in the fiery hearts of stars and scattered across space during explosive supernova events. This realization brings home the truth that we are not separate from the universe, but are made of star stuff, intimately linked to the very processes that govern cosmic evolution. Our cosmic history carries a profound responsibility. It calls on us to pursue knowledge, protect our fragile planet, and reflect on the broader meaning of our existence. As we explore the universe and consider the possibility of life beyond Earth, the awareness of our delicate yet extraordinary place in the cosmos becomes even more urgent. Each discovery enriches our understanding of who we are, where we come from, and how we relate to the vast, timeless universe around us. Ultimately, this journey invites us to take an active part in the unfolding story of existence, recognizing our role within the intricate web of cosmic life. Looking ahead, the long-term survival of humanity within an ever-changing universe presents both daunting challenges and exciting possibilities. These will be shaped by cosmic forces, as well as by our own ability to adapt. As the universe continues to evolve over billions of years, humanity will face critical questions about resource availability, environmental stability, and technological advancement. One promising avenue involves the colonization of space. With conditions on Earth expected to change, whether due to climate shifts, natural disasters, or cosmic events, human populations may one day seek refuge beyond our home planet. Mars, with its relatively accessible resources and the potential to be terraformed, often stands out as a prime candidate for settlement. Other celestial bodies like moons and asteroids could serve as waypoints for deeper space exploration and colonization. Developing the technology for sustainable living in these alien environments will be essential for humanity's expansion into the cosmos. Advanced technologies could offer new solutions for adapting to the universe's evolving conditions. This might include life support systems that draw on local resources from inhospitable settings, or sophisticated artificial intelligence designed to manage complex ecosystems. Biotechnology and genetic engineering could enhance human adaptability, allowing us to survive and thrive on distant planets or within artificial space habitats. The future of humanity is intertwined with the cosmos in ways we are just beginning to understand. Our ongoing quest to explore, adapt, and grow reflects the remarkable journey of life in an ever-expanding universe. Moreover, the long-term survival of humanity may hinge on our ability to anticipate and effectively respond to cosmic threats. These threats include events such as asteroid impacts and powerful solar flares, both of which could have catastrophic consequences if left unchecked. Developing robust defense mechanisms and sophisticated early warning systems will be essential to reduce the risks posed by such phenomena and to safeguard human existence. The quest to understand these cosmic dangers and their potential effects empowers humanity to take timely precautionary measures, bolstering our resilience against uncertain futures. As the universe continues its relentless evolution, presenting new challenges and mysteries, humanity must foster a spirit of collaboration, relentless scientific inquiry, and adaptability. This dynamic will be critical as we navigate the complex path ahead. Our journey through space exploration, ongoing technological progress, and careful stewardship of Earth's environment will play a vital role in ensuring a future where humanity not only survives, but thrives. While uncertainties are an inevitable part of venturing into the unknown, adopting a proactive and forward-thinking approach to cosmic changes can open new pathways for survival and growth in an ever-changing universe. Each step we take toward understanding and embracing the cosmos shapes our place within the vast narrative of existence. Future technologies hold extraordinary promise for advancing our ability to explore and comprehend cosmic processes, potentially enabling humanity to manipulate the very fabric of the universe itself. As scientific knowledge deepens and technological capabilities expand, several promising areas are emerging that could transform how we interact with cosmic phenomena. One of the most exciting prospects lies in astrophysics and space travel technology. Innovations in propulsion systems, such as nuclear thermal propulsion, ion drives, and antimatter engines, could drastically improve our ability to reach distant celestial bodies more efficiently. These advancements would not only facilitate the exploration of planets and moons within our solar system, but also enable missions to neighboring star systems. Advanced telescopes and observational instruments will play a crucial role in gathering detailed information about exoplanets, their atmospheres, and potential biosignatures. This data will be invaluable in assessing the habitability of worlds beyond our own, guiding future exploration and perhaps even the search for extraterrestrial life. Another area of tremendous potential lies in developing technologies to harness and manipulate energy on a cosmic scale. Theoretical concepts like Dyson spheres or Dyson swarms, structures designed to capture the energy output of stars, could provide nearly limitless power for civilization. Engineering projects of this scale would open vast new energy resources, enabling ambitious cosmic endeavors such as terraforming other planets or sustaining large-scale space colonies. In cosmology, breakthroughs inspired by quantum mechanics and general relativity may one day allow us to manipulate gravitational forces. Projects like gravitational wave detection and deeper investigations into dark matter and dark energy are expanding our understanding of the universe's fundamental forces. Such insights could eventually lead to technologies capable of influencing gravitational fields, offering new methods of propulsion or stabilization in regions with intense gravity. Additionally, advances in materials science and nanotechnology could revolutionize our ability to build structures and habitats in space. By efficiently utilizing in-situ resources, such as mining asteroids for metals or using lunar soil, regolith, as construction material, humanity could establish self-sustaining colonies or outposts throughout the solar system. This expansion would dramatically increase our presence in space and enhance our ability to thrive beyond Earth. Crucially, the integration of artificial intelligence and machine learning into these efforts will accelerate our understanding of cosmic phenomena and optimize our strategies for space exploration. With continuous progress in these areas, the prospect of not just exploring but actively shaping our interactions with the cosmos becomes increasingly tangible. While many of these ideas remain theoretical today, each technological breakthrough has the potential to transform our understanding of the universe and our role within it. The possibilities before us are immense, and as we push the boundaries of knowledge and innovation, humanity moves closer to realizing its cosmic future, one shaped by curiosity, ingenuity, and an enduring spirit of exploration. As humanity stands on the threshold of revolutionary technological advancements with the potential to reshape the very fabric of cosmic evolution, a vast and complex array of ethical challenges comes sharply into focus. These challenges reach far beyond our immediate impact on Earth's delicate ecosystems, extending into the profound and largely uncharted territory of manipulating celestial phenomena and cosmic forces. To navigate these ethical dilemmas successfully, society must engage in thoughtful, open dialogue and develop a robust framework centered on responsibility, foresight, and humility. One of the most urgent ethical concerns lies in the environmental consequences of our actions, not only here on Earth, but also beyond, as we contemplate colonizing other planets or exploiting extraterrestrial resources. The prospect of intervening in cosmic processes raises profound questions about the preservation of alien ecosystems, should they exist. If humanity chooses to terraform a barren, inhospitable world, we must seriously consider the ramifications for any existing microbial life or nascent ecosystems. The moral implications of transforming entire planets to suit human habitation demand a delicate balance between our species' needs and the integrity of these distant worlds. This balance is not merely a technical challenge, but a deeply ethical one, requiring respect for the unknown and a commitment to stewardship. The risks involved in manipulating cosmic phenomena themselves are equally daunting. Efforts to harness energy from stars or redirect asteroids for mining purposes carry the potential for unintended and possibly catastrophic consequences. For instance, altering the orbits of celestial bodies could disrupt stable cosmic pathways or even trigger chain reactions leading to astronomical disasters. Such possibilities call for rigorous ethical scrutiny, ensuring that decisions driven by ambition or economic gain do not endanger the stability of the wider cosmos. Every action taken in the name of progress must be carefully weighed against the potential harm it could cause to both our own planet and the vast universe beyond. Furthermore, the uneven distribution of access to these advanced technologies threatens to deepen global inequalities and ignite new conflicts. Whether wielded by nations, corporations, or individuals, the power to influence cosmic evolution raises critical questions about stewardship and justice. Who gets to decide how cosmic resources are allocated? Who benefits from the technological breakthroughs that allow humanity to manipulate the universe on such a grand scale? Addressing these questions will require international cooperation and frameworks that promote equitable access and shared benefits, ensuring that the exploration and utilization of cosmic resources serve the common good rather than narrow interests. These ethical concerns also extend into the philosophical realm, challenging humanity to reconsider its role and responsibilities in the universe. As we gain the power to alter cosmic processes, we must confront profound questions about our place in the cosmos. Do we have the right to take on such immense responsibility? What does it mean to be a steward of the universe, especially given humanity's often destructive history with our own planet? These reflections are not abstract. They shape our collective identity as a species and will influence how we approach the future of cosmic exploration. A proactive and inclusive ethical approach, drawing from diverse voices including scientists, ethicists, and the broader public, is essential to develop a comprehensive understanding of the consequences of our actions and to ensure that our cosmic ventures are guided by respect, responsibility, and humility. Balancing ambition with caution will be vital in defining humanity's cosmic legacy. The vastness of space and the immense scale of cosmic time have long influenced human thought, culture, and philosophy. The universe, estimated to be about 13,800,000,000 years old, dwarfs the fleeting span of human life, which often lasts just a few decades. This staggering perspective challenges our everyday notions of time, significance, and existence, prompting deep reflection on what it truly means to live in such a vast and ancient cosmos. Philosophically, these immense cosmic timescales inspire existential questions about the meaning of human life. The realization of our brief presence within an almost incomprehensibly large universe can provoke feelings of insignificance, leading many to ponder the purpose of life itself. Different philosophical traditions respond to this in various ways, offering interpretations that range from despair to spiritual upliftment. For some, the enormity of the cosmos highlights the fragility and preciousness of life, like fostering a profound appreciation for the connections and experiences that define human existence. Culturally, the universe and humanity's place within it have served as a rich source of inspiration for art, literature, and music throughout history. Artists and writers frequently explore themes of cosmic wonder, exploration, and the unknown to express complex emotions and ideas. The imagery of stars, galaxies, and the infinite cosmos provides a powerful backdrop for exploring human aspirations, fears, and relationships. This artistic engagement reflects a deep-rooted curiosity about the mysteries of the universe and encourages societies to nurture a sense of connection, not only among people, but also with the greater cosmic environment that surrounds us. In facing the extraordinary possibilities and challenges of altering cosmic evolution, humanity stands at a pivotal moment. The choices we make now will shape not only our future, but also the legacy we leave etched across the stars. With thoughtful reflection, ethical commitment, and collective wisdom, we can aspire to become responsible stewards of the cosmos, navigating the infinite unknown with courage, care, and a deep sense of wonder. Additionally, the scientific quest to understand the universe has profoundly shaped cultural stories and worldviews throughout human history. The remarkable progress in cosmology, physics, and astronomy has sparked transformative shifts in how we perceive ourselves and our origins. From early thinkers like Cernus to revolutionary minds such as Darwin and Einstein, these groundbreaking ideas have gradually reshaped humanity's self-image, highlighting the deep interconnectedness of all things and revealing the complex relationships woven throughout the cosmos. This profound shift in perspective resonates powerfully in today's conversations about urgent global issues, including climate change, technological advancements, and our shared responsibilities toward the planet and one another. As we confront the challenges of our cosmic heritage, we are called to rethink our role in the grand tapestry of existence. Moreover, the vastness of space has the power to foster unity among people across cultural, geographic, and political divides. The collective human effort to explore the cosmos, exemplified by international collaborations in space missions and scientific research, sparks a spirit of cooperation and shared aspiration. Celebrating these achievements in uncovering the mysteries of the universe taps into a universal identity, one that transcends borders and encourages a common vision for the future. Ultimately, the immense scale of cosmic time and space serves as a powerful catalyst for reflection on existence, purpose, and our connection to the universe itself. By exploring these profound themes, societies can weave a rich fabric of beliefs, values, and hopes that deepen our understanding of ourselves, while illuminating our ongoing journey through the cosmos. This dialogue between science, philosophy, and culture continues to evolve within the ever-expanding context of cosmic history. With this grand perspective comes a profound responsibility. Humanity must protect and preserve life, guided by an awareness of the fragile and intricate nature of existence. When we consider the sweeping narrative of cosmic evolution, from the birth of stars and galaxies to the emergence of life on Earth, it becomes clear that our actions have far-reaching consequences, shaping the future of life not only on our planet, but potentially across the cosmos. A core aspect of this responsibility lies in recognizing our deep interconnection with the broader web of life. The very elements essential for life were forged in the hearts of ancient stars, and our existence is a direct product of cosmic processes unfolding over billions of years. This understanding calls for a profound respect for the natural world, inspiring us to protect biodiversity and preserve vital ecosystems. The loss of species and habitats disrupts life's delicate balance, and as stewards of Earth, it is imperative that we embrace sustainable practices to safeguard the environment for generations yet to come. Furthermore, the lessons of cosmic history underscore the importance of foresight and caution. Throughout the universe's long evolution, conditions have shifted dramatically, triggering mass extinctions and transforming once hospitable environments into inhospitable realms. Today, humanity faces unprecedented threats, including climate change, habitat destruction, and pollution, many driven by our own actions. Recognizing the potential long-term impacts of these behaviors compels us to become responsible caretakers of life, ensuring we do not unwittingly create conditions that endanger the survival of life as we know it. As humanity extends its reach beyond Earth into space exploration and the possibility of colonizing other planetary bodies, the ethical dimensions of our actions grow even more critical. Should we discover microbial life on other worlds, our responsibility to protect these extraterrestrial ecosystems will emerge as a vital concern. The prospect of altering other planets, whether through terraforming or resource extraction, raises fundamental questions about our role as cosmic caretakers. Ensuring that our activities are guided by respect for the unknown and a commitment to preserving life will be essential to forging an interstellar legacy that honors the delicate balance of existence across the universe. Finally, this profound cosmic awareness inspires a collective spirit rooted in compassion and shared responsibility. It reveals the humbling truth that humanity is but a tiny speck within the immense and indifferent universe. This realization nurtures a deep sense of unity and purpose among us all. When we join forces beyond national boundaries to confront existential dangers and advance efforts to conserve our planet, our collective impact grows exponentially. Together, we can foster a culture that places the preservation of life at its very core. This sense of duty stretches far beyond Earth itself, inviting us to reflect on our place within the vast cosmic community. Understanding the vastness of cosmic history compels us to embrace the responsibility of protecting and sustaining life in all its forms. It demands a profound commitment to safeguarding our fragile planet while honoring the interconnected web that links every living being. By approaching our role as caretakers with wisdom, foresight, and a deep ethical consciousness, we engage in a sacred duty that surpasses the limits of time and space. This sacred responsibility ensures the ongoing continuity of life within the ever-changing, dynamic universe we call home.